In the deep mists of prehistory, long before the famous giants roamed the earth, a monumental chapter was being written, the dawn of the dinosaurs. This era marked not only the rise of creatures that would dominate terrestrial ecosystems for over 160 million years, but also the emergence of extraordinary biological adaptations that have fascinated scientists and enthusiasts alike. Understanding the origins of these prehistoric powers requires us to journey back to the Late Triassic period, around 230 million years ago, a time of significant upheaval and transformation on our planet. The Late Triassic was a world vastly unlike today. Back then, Earth's continents were fused into a supercontinent known as Pangaea, a colossal landmass encircled by a vast global ocean called Panthalassa. The climate was generally hot and dry, with expansive deserts dominating much of the interior lands. Volcanic activity was rife, contributing to fluctuating atmospheric conditions and environmental stress that challenged the survival of many species. In this crucible of change, ecosystems shifted continuously, and evolutionary innovations were the key to survival. Among the many reptiles navigating this dynamic world were the earliest dinosaurs, relatively small, agile creatures that belonged to a group called archosaurs, the lineage that also includes modern crocodiles and birds. These pioneering dinosaurs, like Eoraptor and Herrerasaurus, were modest in size but displayed remarkable versatility. Their evolutionary journey was influenced heavily by their competition. Other reptiles, including the dominant carnivorous redondosaurids and rhynchosaurs, as well as the mammal-like cynodonts. The dawn of the dinosaurs was not sudden, but a gradual ascent facilitated by a series of ecological opportunities. One of the essential advantages these early dinosaurs held was in their limb posture. Unlike sprawling reptiles of their day, dinosaurs had an upright posture with legs positioned under the body. This anatomical innovation allowed for more efficient locomotion, enabling sustained walking and running, which helped them escape predators and hunt more effectively. The upright stance also contributed to greater stamina, a hint of the endurance capabilities that would later characterize many dinosaur lineages. Alongside skeletal advantages, early dinosaurs showed pioneering respiratory designs. Their ancestors' simple lungs developed into more efficient systems, some incorporating air sacs that improved oxygen exchange and reduced body weight. This respiratory adaptation is evident today in modern birds and was a fundamental evolutionary step, leading to the explosive radiation of dinosaurs in succeeding periods. Dietary flexibility further enhanced early dinosauric power. Fossil evidence indicates that some species exhibit omnivorous feeding habits, consuming an array of plants and small animals. This ability to exploit diverse food sources was crucial for survival in competitive habitats and allowed dinosaurs to colonize varied niches. Over millions of years, this adaptability would spawn an incredible diversity of species, from massive herbivores to apex predators. One cannot discuss the origins of dinosaurian power without acknowledging the mass extinction event at the end of the Permian period, which eradicated approximately 90% of marine species and significantly disrupted terrestrial life. This extinction event cleared ecological space, leading to evolutionary radiation in the Triassic. While many reptiles perished, the lineage leading to dinosaurs survived and capitalized on the ecological vacuum, setting the stage for their dominance. In tandem with these external environmental and ecological factors were crucial internal biological developments. Early dinosaurs displayed modifications in their skull fenestration, the arrangement and size of the openings in the skull. These fenestrae served multiple purposes. They reduced skull weight, provided space for muscle attachment, and contributed to the dinosaur's jaw strength and bite mechanics. These anatomical adjustments not only enhanced feeding capabilities, but also supported the metabolic demands of more active lifestyles. It is also worth considering the role of evolutionary experimentation during the dawn of dinosaurs. Various dinosauriforms, relatives close to true dinosaurs, displayed an array of body plans and locomotor adaptations. While many of these experimental forms would eventually vanish, they represent the dynamic evolutionary processes at play, a testing ground from which the successful dinosaurs emerged. The magnificent superpowers archetypal to dinosaurs, such as massive size, armored defenses, extraordinary speed, and refined senses, had their precursors in this formative period. The first sparks of their remarkable biological innovations were lit here, setting the foundation for the extraordinary evolutionary success that dinosaurs would enjoy for tens of millions of years. Moreover, these earliest strides in dinosaur evolution reveal much about the broader patterns of life's resilience and adaptation in the face of planetary-scale changes. The dawn of dinosaurs encapsulates a narrative of survival, ingenuity, and the relentless push of evolution toward greater complexity and specialization. As we move forward to explore the Earth's Mesozoic evolution and how changing worlds shaped dinosaur superpowers, it becomes clear that understanding this dawn is essential. It not only informs us about the origin of these incredible creatures, but also illuminates the dynamic interplay between life and environment, a theme that resonates through every age, including our own. Thus begins the incredible saga of dinosaurian superpowers, born from humble beginnings and set against a world in flux. As we transition from the origins of dinosaurs to a broader panorama, the Earth's Mesozoic era, spanning approximately from 252 to 66 million years ago, emerges as the grand stage where these prehistoric creatures refined and perfected a dazzling array of biological superpowers. This era, neatly divided into the Triassic, Jurassic, and Cretaceous periods, was a time of turbulent planetary transformation and evolutionary innovation. The shifting landscapes, climates, and ecosystems of the Mesozoic not only sculpted the physical forms of dinosaurs, but also catalyzed the evolution of their incredible abilities, allowing them to adapt, dominate, and thrive in an ever-changing world. To appreciate how these ancient superpowers developed, we must first consider the dynamic geological processes at play. The Mesozoic world was defined by the gradual breakup of the supercontinent Pangaea. This monumental tectonic drift began in the early Jurassic and continued through the Cretaceous, fragmenting the vast landmass into separate continents that were slowly moving toward their modern configurations. This tectonic upheaval profoundly influenced the climate, sea levels, and the distribution of habitats, generating isolated ecological niches and environmental pressures that acted as powerful evolutionary drivers. The breaking apart of Pangaea fostered diversification by geographic isolation. Populations of dinosaurs became separated by new oceans and mountain ranges, leading to divergent evolution. In many respects, this speciation was critical in creating the remarkable variety of dinosaur species with specialized traits adapted to their unique environments. For instance, dinosaurs in the lush, humid jungles of what is now South America evolved differently from their contemporaries, inhabiting the arid regions of what is now North America or Asia. Climate fluctuations were another potent force shaping dinosaur evolution. The Mesozoic climate was generally warmer than today, with high levels of atmospheric carbon dioxide and little to no polar ice caps, resulting in higher sea levels that flooded continental interiors. However, the climate was not static. It experienced periods of warming and cooling, fluctuating humidity, and changes in rainfall patterns. These environmental rhythms imposed selection pressures that required dinosaurs to evolve physiological and behavioral adaptations, some of which were truly extraordinary. One such adaptation was thermoregulation, the ability of animals to control their body temperature. During the Mesozoic, as ecosystems ranged from humid rainforests to desert-like environments, the capacity for temperature regulation became vital. Although dinosaurs are traditionally viewed as cold-blooded due to their reptilian heritage, recent research suggests that many species may have had complex metabolic strategies, exhibiting traits of warm-bloodedness or a unique intermediate that allowed them to be more active in varied climates. Feathers, initially emerging for insulation or display, may in fact have played a significant role in helping regulate body temperature. The partitioning of ecosystems also drove dietary specialization. Herbivorous dinosaurs developed diverse feeding strategies, and carnivorous species adapted with evolving hunting skills and sensory enhancements. The herbivores, such as hadrosaurs with their elaborate dental batteries, adapted to efficiently process tougher and more fibrous plants that proliferated during the Cretaceous, including conifers and early flowering plants. These botanical changes likely created new ecological challenges and opportunities, fueling evolutionary arms races between plant eaters and carnivores alike. Moreover, the ever-changing Mesozoic landscapes encouraged the evolution of complex locomotor adaptations. As forests grew denser or plains expanded, dinosaurs evolved to exploit various modes of movement. Some became sprinters capable of bursts of speed to escape predators or chase prey, such as ornithomimids, while others developed colossal size to deter attackers and browse high vegetation, exemplified by sauropods. These physical adaptations were not born in a vacuum, but in constant response to shifting environmental demands. The evolution of sensory superpowers also illustrates the impact of Mesozoic environmental dynamics. In responding to increasingly competitive and complex ecosystems, many dinosaurs enhanced their vision, hearing, and olfactory senses. For example, theropods developed stereoscopic vision for depth perception crucial in hunting, while others exhibited large olfactory bulbs indicating a keen sense of smell. These sensory capabilities were vital for communication, locating food, and predator avoidance. Interestingly, the Mesozoic was also a period of major evolutionary experimentation as dinosaurs and other creatures developed specialized defensive strategies. Armor plating, tail clubs, horns, and crests emerged in various species, providing not only physical protection but also mechanisms for visual display and intra-species signaling. These features often arose in response to predation pressures and social behaviors intricately linked to the changing environmental landscape. Another pivotal factor during the Mesozoic was the rise of flowering plants, or angiosperms, which first appeared in the early Cretaceous. This botanical revolution transformed ecosystems by adding new sources of food and altering habitats dramatically. Dinosaurs that could exploit these novel resources found considerable advantages, leading to further diversification and adaptation. The coevolution of plants and herbivores showcases one of the most fascinating biological interactions of this period. The Mesozoic era was not without its trials. Shifting ocean currents, volcanic activity, and asteroid impacts periodically disrupted ecosystems, testing the resilience and survival strategies of dinosaurs. These events added layers of environmental complexity that demanded flexible and innovative responses, from migratory behaviors to reproductive adaptations such as nesting strategies and parental care. In synthesizing these diverse elements, we see that the Mesozoic Earth was a crucible of change that forged dinosaurian superpowers. Geological forces fragmented habitats, climate oscillations challenged physiology, ecological competitions honed survival skills, and botanical revolutions expanded dietary possibilities. Together, these factors intertwined to shape the evolutionary narrative of dinosaurs, leading to an extraordinary tableau of life forms uniquely equipped to navigate their complex, ever-changing world. As we continue exploring the fascinating adaptations that flowed from these Mesozoic dynamics, including the remarkable skeletal innovations enabling flight, we gain deeper insight into how life on Earth has repeatedly responded to change with ingenuity and resilience. The story of the dinosaurs during this period becomes not only a tale of ancient creatures, but a profound lesson in the power of environmental interaction, shaping evolutionary potential. As we delve deeper into the intricate tapestry of dinosaur evolution, one of the most fascinating and transformative chapters unfolds around the concepts of fenestration and flight, key milestones that collectively illustrate the origins of some of the most remarkable adaptations in dinosaurian history. This section invites us to explore how openings in the skull, known as fenestrae, paved the way for a suite of anatomical innovations, including the extraordinary leap from terrestrial locomotion to the skies, culminating in the first feathered flyers, and, ultimately, the avian dinosaurs that gave rise to modern birds. To begin, the term fenestration in paleontology refers specifically to the presence of openings in the skull bones. These fenestrae are more than just empty spaces. They are critical evolutionary features that served multiple functional advantages. Early archosaurs, the broader group that includes dinosaurs, exhibited various skull openings that reduced the weight of the skull and provided additional surface area for the attachment of powerful jaw muscles. This configuration enhanced bite strength and jaw mobility without compromising structural integrity. Among dinosaurs, the pattern and number of these fenestrae became diagnostic traits, supporting taxonomic differentiation and illustrating evolutionary relationships. The diapsid skull design, characterized by two temporal fenestrae on each side of the skull, was a defining feature of most dinosaurs. The strategic placement of these openings enabled muscle bulging and allowed dinosaurs to develop stronger, more efficient bites, which was a crucial superpower in both predation and defense. But fenestration's evolutionary importance stretches far beyond jaw mechanics. These openings also likely played an essential role in cranial kinesis, the ability of skull bones to move relative to each other. This capability can enable animals to better manipulate food, swallowing it more efficiently, or processing it with greater specialization. Within some dinosaur lineages, notably in theropods and ornithischians, this feature evolved to varying degrees, offering enhanced feeding versatility. The story becomes even more compelling when we consider how these skull adaptations set the stage for the evolution of feathers and flight. Around the Middle to Late Jurassic period, fossil discoveries have revealed theropod dinosaurs bearing primitive feathers, indicating that feathers initially evolved not for flight, but possibly for insulation, display, or brooding. This aligns with the finding that many of these feathered dinosaurs still retained the characteristic fenestrated skulls, linking cranial adaptations with integumentary, skin and feather innovations. Furthermore, the anatomy necessary for powered flight required a complex integration of traits. Forelimb modifications, lightweight skeletons, and a high metabolic rate converged in certain Maniraptoran theropods, a group that includes dromaeosaurs and the earliest birds. These dinosaurs display significant skeletal fenestration, such as large antorbital fenestrae, openings in front of the eyes that reduced skull mass. This contributed to overall weight saving necessary for flight. The evolution of the shoulder girdle and wrist bones also reflects this trend, allowing for the extensive wing movement essential to powered flight. The transformation from fingers to wing feathers represents a pinnacle of functional adaptation, but it took millions of years of incremental changes growing from these foundational anatomical innovations. Among the most famous early flyers is Archaeopteryx, discovered in the late Jurassic strata of Germany. Possessing a mosaic of reptilian traits, such as teeth and a long bony tail, alongside avian features like asymmetrical flight feathers and a wishbone, furcula. Archaeopteryx embodies the transitional form bridging non-avian dinosaurs and birds. Its skull fenestration patterns preserve those early dinosaurian characteristics, reinforcing the deep evolutionary ties between dinosaurs and modern birds. Flight conferred numerous superpowers: the ability to escape predators swiftly, exploit new ecological niches inaccessible to ground-bound competitors, and expand geographic ranges. Feather evolution, nurtured by prior anatomical shifts including fenestration, also brought advances in thermoregulation and sophisticated communication via plumage coloration and patterns. The fossil record continues to yield astonishing finds such as Microraptor, a small four-winged dromaeosaur from the early Cretaceous of China. Microraptor's unique feather arrangement on both its forelimbs and hind limbs suggests gliding capabilities, marking an evolutionary experiment in flight before the emergence of true powered flyers. The retention of fenestrated skull features in such species highlights the persistence of these primitive traits alongside novel ones. Understanding fenestration also sheds light on the evolutionary constraints and trade-offs dinosaurs faced as they adapted. Reducing skull weight was beneficial for flight, but it also demanded a balance to maintain protective strength and structural function. This balance influenced sensory development and braincase evolution, influencing ecological performance and behavior. As the Mesozoic progressed, the diversification of dinosaur lineages led to varying degrees of these adaptations. While many non-avian dinosaurs retained sturdy skulls with robust fenestrae supporting their predatory or herbivorous lifestyles, the lineage that led to birds progressively refined skeletal and muscular features conducive to aerial mastery. In conclusion, the origins of dinosaurian adaptations such as fenestration and flight reveal a profound narrative of evolutionary innovation, resilience, and experimentation. The skull's fenestrae were not merely structural curiosities, but instrumental adaptations that opened functional possibilities, from enhanced feeding mechanics to enabling the weight-saving necessary for flight. This journey from terrestrial reptiles to soaring avians exemplifies the dynamic interplay of form and function, environment and biology. As we transition into examining the armored titans of the dinosaur world in our next section, these themes of adaptation and survival through specialized traits persist, underscoring the multitude of biological strategies that made dinosaurs extraordinarily successful for millions of years. The story of fenestration and flight is but one spectacular thread woven into the incredible fabric of dinosaurian superpowers. In the vast and dynamic ecosystems of the Mesozoic era, where colossal predators prowled and towering herbivores grazed, there existed a group of dinosaurs that seemed to embody the very essence of resilience and defense: the ankylosaurs. Often referred to as the living tanks of the dinosaur world, ankylosaurs evolved some of the most formidable natural armor ever seen in the animal kingdom. Their story is a testament to the power of evolutionary adaptation, demonstrating how biological fortification and weaponization could become a central superpower in the relentless struggle for survival. To truly appreciate the armor of ankylosaurs, we must first understand their place within the dinosaur family tree. Ankylosaurs belong to the Ornithischia order, a diverse clade of herbivorous dinosaurs united by unique pelvic structures most conducive to a quadrupedal gait. Within Ornithischia, ankylosaurs comprise a subgroup known as Ankylosauria, characterized by their distinctive osteoderms, bony plates embedded within the skin that form an extensive protective shield. The early ankylosaurs emerged during the Late Jurassic period, around 160 million years ago. But it was during the Cretaceous period that they truly flourished and diversified across what are now North America, Asia, and Europe. This geographic spread corresponds with the fragmentation of continents we explored earlier, which fostered diverse habitats and ecological niches where ankylosaurs could evolve specialized adaptations. One of the crowning features of ankylosaurs was their remarkable osteoderm armor. These were not mere superficial scales, but intricate mosaic-like arrays of bony plates, often fused to the underlying bones, creating an almost impenetrable exoskeleton. The armor covered their backs, flanks, and even parts of the skull, serving as a static but highly effective defense against predators. In some species, such as Ankylosaurus magniventris, the armor was so dense and extensive that it essentially turned the entire body into a formidable fortress. Adding to their defensive repertoire was the evolution of tail weapons. The iconic tail club, seen in many ankylosaurids, was a mass of enlarged, fused osteoderms at the tail's end, forming a powerful blunt instrument. This mace could be swung with tremendous force to discourage or injure attacking theropods. Biomechanical studies suggest these tail clubs could produce blows comparable to the crack of a baseball bat, an impressive feat for an animal weighing several tons. The structural complexity of ankylosaur tails extended beyond the club. Strong, ossified tendons along the tail provided stiffness and support, greatly enhancing their ability to deliver powerful lateral swings without compromising balance or control. This defensive tail weapon represents a remarkable evolutionary convergence between offense and defense, transforming a typically passive feature into an active tool for survival. Of course, armor and tail clubs alone do not tell the full story of ankylosaur superpowers. Their robust and low-slung body shapes contributed not only to defense, but also to stability, allowing them to maintain a low center of gravity that made it difficult for predators to flip or topple them. Their limbs were sturdy and well-built, designed to support their heavy armor and distribute their weight efficiently during slow, steady movements. Ankylosaurs also displayed intricate cranial structures. The skulls were often covered with bony nodules and plates, some species even developing horns or spikes above the eyes and along the jawline. These cranial armaments likely served multiple roles as protectors of the head, displays for species recognition, or deterrence mechanisms signaling to potential threats. Underneath this fortress-like exterior lay hints of less obvious superpowers. Despite their bulk, ankylosaurs were not merely defensive tanks. Their sensory systems, inferred from well-preserved fossils, indicate an enhanced sense of smell and hearing. These adaptations would have been vital for detecting predators or communicating within their social groups. In addition, some evidence suggests that ankylosaurs may have possessed keratinous beaks, adept at cropping low-lying vegetation, further underscoring their evolutionary success as herbivores. Interestingly, the development of such robust armor and weaponry likely co-evolved with the presence of large theropod predators such as Tyrannosaurus rex and other carnivorous dinosaurs. This predator-prey arms race created an evolutionary pressure cooker, driving ankylosaurs to evolve ever more elaborate defenses while predators refined their offensive tactics. The interplay between these titanic adversaries is among the most captivating dynamics of the late Cretaceous ecosystems. In the context of paleoecology, ankylosaur armor might have also functioned beyond mere defense. Some scientists propose roles in thermoregulation, with blood vessels possibly running through the osteoderms facilitating heat exchange. Others speculate that the armor, with its varied shapes and textures, played roles in species recognition and sexual selection, contributing to complex behavioral displays within ankylosaur communities. When we examine the fossil record, The abundance of ankylosaur specimens and their distinct footprints across multiple continents testify not only to their armored might, but also to their ecological success. Their evolutionary strategy of emphasizing defense over speed is a fascinating contrast to other dinosaur superpowers, like the predatory speed and agility of velociraptors or the towering reach of sauropods. The armored titans of the Mesozoic ultimately illustrate a vital lesson from nature: that power and survival can emerge not only from aggression and size, but also from impenetrable defense and unyielding resilience. Ankylosaurs remind us that the capacity to endure through time is a superpower etched into the very bones, a testament to evolutionary ingenuity in the face of unstoppable threats. As we continue our journey through the world of dinosaurs, the next chapter unveils the enigmatic Spinosaurus, a creature that redefined aquatic adaptations among terrestrial giants. From living tanks to swimming monsters, the diverse strategies harnessed by dinosaurs to wield their prehistoric superpowers reveal an astonishing spectrum of life's creativity and tenacity on ancient Earth. Nestled within the intricate web of dinosaur evolution lies one of the most mesmerizing and enigmatic giants to have ever graced our planet: Spinosaurus aegyptiacus. This colossal dinosaur, distinguishable by its towering sail-like structure and unique semi-aquatic adaptations, challenges many traditional notions of what it meant to be a dinosaur. As we explore the superpowers of Spinosaurus, we unveil a creature finely tuned by evolution to master both land and water, blending terrestrial might with aquatic agility in an unprecedented evolutionary symphony. Spinosaurus lived during the mid to late Cretaceous period, approximately 112 to 93 million years ago, primarily across what is today North Africa. For decades, it stood out as the longest known carnivorous dinosaur, with specimens suggesting lengths exceeding 15 meters, potentially rivaling or even surpassing the famed Tyrannosaurus rex in sheer size. But size alone does not capture what truly set Spinosaurus apart. The very form and function of its anatomy reveal a range of adaptations that portray it as a semi-aquatic predator, arguably the first dinosaur to occupy such a lifestyle. One cannot discuss Spinosaurus without first focusing on its towering neural spines that projected from its vertebrae. These elongated spines, some measuring over 1.6 meters, merged to form the iconic sail-like structure along its back. While the exact purpose of this sail remains a subject of ongoing research and debate, several plausible hypotheses exist. It could have served as a display structure to attract mates or intimidate rivals, an efficient thermoregulatory system assisting in heat dissipation or retention, or even a hydrodynamic aid for swimming. Regardless of the precise function, the sail unmistakably represents a key superpower, setting this dinosaur apart visually and functionally from its contemporaries. The morphology of Spinosaurus's skull provides further insight into its aquatic prowess. Unlike the broad and robust skulls common among many terrestrial theropods, Spinosaurus possessed a long, narrow, crocodile-like snout filled with conical, non-serrated teeth, ideally suited for grasping slippery prey like fish. This rostral adaptation indicates a diet heavily focused on aquatic organisms, consistent with a lifestyle involving hunting in rivers and coastal environments. The presence of pressure-sensitive nerve endings in its snout, similar to those seen in modern crocodilians, would have enabled Spinosaurus to detect movements and vibrations in the water, an invaluable sensory superpower for locating prey in murky aquatic habitats. Supporting this semi-aquatic lifestyle, recent discoveries and analyses of Spinosaurus fossils reveal limbs and skeletal structures specialized for swimming. Unlike most large theropods with strong hind limbs built for running, Spinosaurus's hind limbs were shorter and more robust, culminating in broad, flat feet that likely aided in paddling through water. Its dense limb bones, an adaptation known as pachyostosis, would have increased overall body density, facilitating submersion and underwater stability, much like modern diving birds and aquatic reptiles. Further reinforcing its affinity for aquatic environments is the discovery of enormous, broad feet, as well as a tail markedly different from other theropods. Detailed reconstructions based on newly examined fossils suggest that Spinosaurus sported a deep, laterally compressed tail with tall neural spines, forming what appears to be a large paddle-like structure. This powerful fin-like tail would have been instrumental for propulsion and maneuverability in water, granting Spinosaurus a swimming capacity unmatched by other predatory dinosaurs. This semi-aquatic prowess would have given Spinosaurus a whopping superpower: the ability to exploit niches inaccessible to the large terrestrial predators of its time. It could hunt in rivers, lakes, and coastal shallows, feasting on large fish such as ancient coelacanths and sawfish-like creatures, reducing direct competition with other apex carnivores. Thus, Spinosaurus exemplifies evolutionary innovation by venturing into new ecological territories. However, its adaptations did not forfeit its terrestrial capabilities entirely. Though built differently from classic bipedal runners, Spinosaurus likely moved on land in a quadrupedal manner, supported by its robust forelimbs equipped with massive hooked claws. These claws could have aided in digging for prey or defense, highlighting dual functionality, an evolutionary compromise blending aquatic specialization with terrestrial survival. The discovery history of Spinosaurus itself mirrors its own enigmatic nature. Unearthed first in 1912 in Egypt, much of the original material was destroyed during World War II, leaving paleontologists with limited evidence for decades. Only recently, with new fossil finds in Morocco and advanced imaging technology, have researchers begun reconstructing its full anatomy, revealing the true scale of its unique adaptations. From an evolutionary perspective, Spinosaurus challenges preconceived limits assigned to dinosaurs. It demonstrates that these ancient reptiles were not strictly land-bound giants, but could also master semi-aquatic realms, developing morphological superpowers akin to modern crocodilians or otters, but on a truly massive scale. Its sail, specialized skull, paddle-like tail, and dense bones all represent integrated adaptations that enabled Spinosaurus to thrive in its environment. Together, they embody a complex biological toolset forged through millions of years of natural selection, a masterclass in evolutionary innovation and the power of adaptation. Understanding Spinosaurus's superpowers enriches our broader appreciation of how dinosaur lineages diversified and succeeded. It reminds us that the dinosaurian story is not just about brute force or speed, but also about versatility, niche exploitation, and the exquisite morphological creativity that life employs to survive and prosper. As we continue to explore other remarkable dinosaur adaptations, we will next venture into the deadly precision of Velociraptor's sickle claw, an entirely different superpower, but one no less fascinating. From aquatic giants to stealthy predators, the spectrum of dinosaurian abilities showcases nature's astonishing capacity for innovation across millions of years. Velociraptor, a name synonymous with swiftness, cunning, and deadly precision, has fascinated paleontologists and the public alike for decades. While popular culture has often dramatized this small but ferocious dinosaur, the reality behind its iconic sickle-shaped claw is even more compelling and remarkable. This single evolutionary adaptation encapsulates a suite of biomechanical innovations that rendered Velociraptor one of the most fearsome predators of its time. A superpower not of brute strength but of surgical efficiency. Velociraptor existed during the late Cretaceous period, approximately 75 to 71 million years ago, inhabiting the arid and semi-arid regions of what is now Mongolia and northern China. Compared to the oversized theropods like Tyrannosaurus rex or Giganotosaurus, Velociraptor was relatively small, measuring about 2 meters in length and standing roughly half a meter tall at the hip. However, its size belied its lethality, largely thanks to one extraordinary anatomical feature: the enlarged second toe claw. This claw, often referred to as the sickle claw, was highly curved, razor-sharp, and could reach lengths of over 9 centimeters, 3.5 inches. Unlike the other toes, the second toe's claw was held off the ground while walking, preventing wear and maintaining its deadly sharpness, a clear sign of its specialized function. The evolutionary purpose of this claw has been extensively debated, but growing evidence points to a role as a precision weapon used in hunting and combat. Biomechanical studies suggest that the sickle claw was deployed with incredible dexterity. Velociraptor could raise this claw and use it to deliver slashing attacks or gripping punctures to prey, targeting vulnerable areas such as the neck or abdomen. The curvature and sharpness allowed it to inflict deep wounds with minimal force, much like a surgical blade. This precision made Velociraptor particularly effective in hunting smaller to mid-sized prey, including mammals, smaller dinosaurs, and possibly scavenging opportunities as well. What made this claw even more lethal was the locomotor and muscular adaptations supporting its use. Velociraptor's leg structure provided both agility and strength. It had long, slender legs ideal for rapid acceleration, sharp turns, and ambush-style attacks. Strong flexor muscles enabled quick deployment and powerful retraction of the sickle claw during a strike. Additionally, its flexible wrist and arm joints allowed it to grapple and hold struggling prey with its forelimbs while delivering claw attacks with its feet. Some fossil specimens even preserve evidence of quill knobs on Velociraptor's forearms, indicating the presence of feathers, a clue to its probable agility and the potential for complex behavioral displays or brooding. Feathers might also have contributed to stealth during hunting, muffling sound, and improving balance and maneuverability. Paleopathological evidence lends further insight into the claw's use. Fossils with healed wounds and bite marks imply Velociraptor engaged in confrontations, whether with prey or rival velociraptors, showcasing its claw as both an offensive and defensive tool. This evolutionary weapon was precise, but also part of a broader predatory toolkit that included sharp teeth, stealth, and pack behavior, enabling Velociraptor to fill the niche of a swift and intelligent predator. The precision sickle claw was not unique to Velociraptor alone, but is a hallmark of the Dromaeosauridae family, a group of feathered theropods known for their hunting prowess. However, Velociraptor's sickle claw remains one of the most studied and emblematic examples of this remarkable evolutionary innovation, reflecting the intricate relationship between form, function, and survival. Understanding the deadly precision of Velociraptor's claw offers a window into the complexity of predatory behaviors in the dinosaurian world and the evolutionary arms race that shaped them. This claw represents more than just a weapon. It epitomizes how evolution refined specific traits into highly specialized tools, deepening our appreciation for the diversity of dinosaur superpowers. As we continue our journey into dinosaur adaptations, the next chapter will examine theropod teeth, serrated blades, and the ongoing debate surrounding their bite force. This exploration will illuminate yet another facet of dinosaurian predatory capabilities, enhancing our understanding of their evolutionary mastery in the ancient ecosystems they once ruled. Among the myriad superpowers that dinosaurs wielded throughout the Mesozoic, the weapons of choice for theropods, the fierce, primarily carnivorous group to which species like Tyrannosaurus rex and Velociraptor belonged, were their teeth. These formidable teeth, often likened to serrated blades, were far more than mere tools of consumption. They were specialized instruments, finely honed by millions of years of evolution, embodying a combination of cutting power, durability, and versatility that played a crucial role in theropods becoming apex predators of their time. The typical theropod tooth was conical to blade-shaped with sharp edges, serrated much like a steak knife. These serrations, called denticles, functioned to slice through flesh, muscle fibers, and even bone, allowing the dinosaur to inflict lethal wounds efficiently. Unlike the simple, peg-like teeth of some other reptiles, theropod dentition represented a complex adaptation that optimized both prey capture and processing. The evolutionary origins of serrated teeth in theropods can be traced back to earlier carnivorous archosaur ancestors, but dinosaurian theropods perfected and expanded this trait, exhibiting a remarkable diversity in shape, size, and arrangement. Different species adapted their teeth for specialized diets and hunting methods. For example, the robust, thick teeth of Tyrannosaurus rex were capable of crushing bone, earning it the reputation of a bone-crushing predator, whereas the slender, recurved teeth of dromaeosaurs were ideal for gripping and slicing softer tissues. Central to the discussion of theropod teeth is the ongoing debate about their bite force. Scientists have used various methods, from biomechanical modeling and computer simulations to extrapolations based on muscle attachment sites and fossilized jaw robustness, to estimate the strength of the bite delivered by various theropods. Tyrannosaurus rex, in particular, stands out in this conversation, with estimates suggesting one of the strongest bite forces of any terrestrial animal, ranging as high as 35,000 newtons or more. Such a powerful bite would allow T. rex to crush large bones and access nutritious marrow, an advantage both for hunting and scavenging. However, debates persist regarding the full extent of this bite force and how it compared to other large theropods, such as Giganotosaurus and Carcharodontosaurus. While not able to bite with as much sheer power, these other carnivores may have compensated with sharper teeth designed for slicing rather than crushing. This divergence in feeding strategies illustrates how different superpowers can manifest even among apex predators, balancing strength, speed, and precision. Furthermore, fossil evidence reveals wear patterns, breakage, and even healing in theropod teeth, indicating frequent use under intense physical demands. The capacity for teeth replacement, common in theropods, ensured their effectiveness over the animal's lifetime. Replacement teeth grew in cycles, and this continual renewal shielded them from the detrimental effects of damage, maintaining their serrated edge and hunting efficiency. In addition to structural design, the positioning and arrangement of teeth also contributed to their effectiveness. Theropod jaws were equipped with rows of teeth that allowed them to clamp onto struggling prey firmly. The serrated edges did not just cut flesh, but also worked to reduce the prey's ability to break free by creating deep wounds that caused shock and blood loss. Some evidence suggests certain theropods might have employed a puncture and pull feeding strategy, using their teeth to latch onto prey and then pull backward to tear flesh, a method that requires precise control and powerful musculature. The role of teeth extended beyond feeding into social behaviors and intraspecific competition. Bite marks on theropod fossils from rivals indicate that teeth were used not only for hunting, but also in confrontations with competitors or rivals during dominance disputes and mating contests. This multiplicity of uses further emphasizes the evolutionary significance of serrated teeth as multifunctional tools. Recent advances in paleontology have also introduced the concept that some theropods might have had complex sensory adaptations associated with their jaws and teeth. For instance, Sensitivity around the snout area could have allowed early detection of prey or nuanced manipulation during feeding. Such sensory enhancements, although speculative, would add another layer to the superpower of theropod teeth. Not only were they physically formidable, but potentially integrated into a finely tuned neuromuscular system, enhancing hunting precision. In summation, the theropod teeth, those serrated blades of prehistoric times, represent a blend of evolutionary refinement, structural integrity, and functional versatility that propelled these dinosaurs to the pinnacle of predation. While the debate on the exact magnitude of their bite force continues to evolve with new technological and fossil discoveries, the importance of these teeth as symbols of predatory superpowers is irrefutable. This narrative of adaptation and power serves as a prelude to exploring the sensory world of dinosaurs, their vision, hearing, and smell, which further amplified their ability to survive and dominate. As we continue our exploration of dinosaurian superpowers, the marvels of predatory teeth remind us that nature's designs are as diverse as they are ingenious. Imagine a world 66 million years ago, teeming with giants whose survival depended not just on strength or size, but on an extraordinary array of sensory superpowers. Dinosaurs, though often portrayed as lumbering and somewhat simple creatures, possessed senses that stretched far beyond human comprehension. Eyes finely tuned to their environments, ears adapted to detect subtle sounds, and noses capable of inhaling a spectrum of hints that shaped their perception of the prehistoric world. This exploration into dinosaur vision, hearing, and smell uncovers a realm of sensory sophistication that was crucial for hunting, avoiding predators, social interaction, and environmental awareness. Let us begin with vision, often regarded as the primary sense for many predatory dinosaurs. Fossilized skulls, specifically the size and placement of the orbits, the eye sockets, offer clues about visual acuity. Theropods, the group that includes fearsome hunters like Tyrannosaurus rex and Velociraptor, often had large orbits positioned forward on the skull, providing overlapping fields of view known as binocular vision. This stereovision was essential for depth perception, allowing precise estimation of prey distance and enhancing striking accuracy. Studies on scleral rings, bony rings supporting the eyes preserved in some dinosaur fossils, have provided additional information about their visual capacities. The presence and size of these structures suggest that many dinosaurs had large eyes with excellent light sensitivity, enabling activity during dawn, dusk, or even low light conditions. This adaptability would have granted them advantages in hunting or avoiding threats in twilight hours. Moreover, variations in eye shape and positioning imply diverse ecological roles. Herbivorous dinosaurs, such as hadrosaurs, typically had eyes placed more laterally, affording an extended field of view to monitor for predators while grazing. This panoramic vision was invaluable for early threat detection, trading some depth perception for a broader surveillance range. Dinosaurs may have also had color vision, hinted at by the structure of photoreceptive cells in modern birds, their closest living relatives. Color vision would have played important roles in foraging, mate selection, and social signaling, particularly in species displaying colorful feathers or skin patches. Moving to hearing, dinosaur auditory systems exhibit remarkable complexity and diversity. The structure of the inner ear, particularly the cochlea, a spiral-shaped organ responsible for auditory processing, found in well-preserved fossils, reveals that some dinosaurs had acute hearing abilities. For example, troodontids, small feathered theropods, possessed elongated cochlea, indicating an ability to hear a broad range of frequencies, including very high-pitched sounds. This auditory acuity suggests several ecological implications. It could have facilitated nuanced communication between individuals, warning calls of predators, or detecting prey movements concealed by vegetation or darkness. In larger theropods, such as Tyrannosaurus rex, sensitivity to low-frequency sounds has been proposed, potentially allowing communication over long distances through infrasound, experience modern elephants and some whales share. Such abilities would have created complex social dynamics, territorial behaviors, or mating strategies. Examining the external ear's role is challenging due to the rarity of soft tissue preservation, but the shape of the skull apertures and jaw bones provides indirect evidence. Pathways for sound conduction reveal that some species could discern directional cues, essential for locating prey or rivals. These abilities would complement their keen vision and sharpen their predatory or defensive capabilities. Perhaps the most astounding sensory superpower in dinosaurs was their sense of smell. The olfactory bulbs, the brain regions tasked with processing scent, are well preserved in endocasts, natural molds of brain cases of many dinosaur species. Carnivorous theropods often had large olfactory bulbs, indicating an exceptional sense of smell. Tyrannosaurus rex stands out, its olfactory bulbs proportionally among the largest known for any dinosaur, suggesting it could detect scents over vast distances. This trait would have been invaluable for scavenging carcasses, locating prey hidden in dense vegetation, or even tracking mates. Some hadrosaurs and ceratopsians, while less renowned for predation, showed olfactory capabilities that supported social interaction and environmental awareness. Furthermore, the nasal cavity's complexity in some dinosaurs hints at advanced functions. Certain groups displayed intricate nasal turbinates, bony structures that likely helped warm and humidify air, potentially increasing olfactory sensitivity. These features align with the idea that dinosaurs had metabolic rates necessitating such adaptations, linking sensory prowess with physiology. Combining these senses, vision, hearing, and smell, dinosaurs possessed a multisensory system finely tuned to their unique lifestyles. For carnivores, this translated to deadly efficiency, stalking prey under low light, detecting faint sounds, or tracking scents over great distances. Herbivores leveraged these senses for vigilance, social cues, and resource location. Importantly, sensory adaptations were not static across the Mesozoic, but evolved in response to ecological pressures. As new predators emerged and environments shifted, sensory modalities co-adapted. Feathered dinosaurs may have developed ultraviolet vision facilitating intraspecific communication or improved camouflage detection. Social species likely relied more on vocal communication, necessitating refined hearing. In summary, exploring the senses of dinosaurs opens a window into a world vibrant with life and sensory complexity. Their vision, hearing, and olfaction were superpowers in their own right, enabling survival, reproduction, and dominance in a perilous prehistoric landscape. This sensory mastery complements the physical adaptations previously discussed, painting an extraordinary portrait of dinosaurs not merely as brute beasts, but as highly sophisticated organisms deeply attuned to their environment. As we proceed, our journey will next take us skyward to the towering Camarasaurus and the sauropod supernecks, marveling at how evolutionary ingenuity allowed these giants to reach for the sky, continuing the ever-expanding narrative of incredible dinosaurian superpowers. In the breathtaking expanse of the Jurassic period, among the most awe-inspiring creatures to ever grace our planet were the sauropods, giant, long-necked herbivores that ruled the landscape with an unparalleled combination of immense size and graceful stature. At the heart of this group stands Camarasaurus, a genus whose name means chambered lizard, revealing a defining feature of its skeletal design: vertebrae built with hollow chambers to reduce weight yet retain strength. This adaptation was critical to support one of nature's most astounding evolutionary marvels, the sauropod superneck. Camarasaurus roamed the lush floodplains and forested regions of North America during the Late Triassic, approximately 155 to 145 million years ago. Measuring around 18 meters in length and boasting a sturdy body, it was not the longest sauropod, but is one of the best understood, thanks to an abundance of well-preserved fossil specimens. Its neck, while modest compared to some of its colossal relatives, could reach lengths of up to 4.5 meters, allowing it to reach and browse vegetation inaccessible to many other herbivores. But what made the sauropod neck a true superpower? To understand this, we must explore the complex interplay of anatomy, physiology, and ecology that enabled sauropods like Camarasaurus to evolve such extraordinary appendages. Firstly, the structural design of the sauropod vertebrae was revolutionary. The vertebrae were not simple solid bones, but rather pneumatically expanded, containing large air sacs and hollow spaces. This ingenious adaptation significantly reduced the neck's overall weight while preserving structural integrity, a crucial balance for managing the mechanical stresses associated with supporting and moving such a long and heavy structure. These air sacs were connected to the respiratory system, a trait shared with modern birds, suggesting an efficient system for oxygen exchange and thermoregulation. Lightened yet strong neck bones, supported by a network of ligaments and muscles, allowed Camarasaurus to raise, lower, and sweep its neck with remarkable control and energy efficiency, minimizing fatigue during feeding. Physiologically, sustaining a long neck required adaptations beyond the skeleton. The circulatory system had to be powerful enough to pump blood all the way to the brain against gravity, a task demanding a large, high-pressure heart and specialized vascular adaptations, such as valves preventing backflow. While direct evidence is scant, these inferences are supported by biomechanical models and comparisons to large modern animals. From an ecological perspective, the sauropod superneck expanded feeding reach dramatically. Unlike smaller herbivores confined to ground-level plants, Camarasaurus could access higher vegetation, such as conifers, cycads, and enormous ferns, often brushing leaves from tall trees without moving its massive body. This feeding strategy reduced competition and allowed exploitation of an abundant but previously underutilized resource layer. Moreover, the neck's flexibility contributed to versatile feeding habits. Although often visualized stretching high to pluck leaves from the tallest branches, geological and anatomical research indicates that sauropod necks, including the Camarasaurus, were capable of sweeping horizontal ranges, scanning vast areas of plant matter with minimal energy expenditure. This efficient browsing technique further underscores the neck's role as a superpower in survival. Intriguingly, the neck's length and use might also have played roles in social and reproductive behavior. Long necks may have been used for visual display, species recognition, or even combat, akin to modern giraffes' necking battles. These behaviors suggest that the superneck was both a functional feeding adaptation and a signal in social dynamics. The evolution of such extraordinary necks was not without challenges. Paleontologists have long debated the mechanical feasibility of sustaining and mobilizing such lengthy structures. Yet, the fossil record of Camarasaurus and other sauropods demonstrates that evolutionary pressures shaped a precise balance of strength, flexibility, and energy efficiency. Indeed, Camarasaurus's relatively moderate neck length compared to giants like Brachiosaurus or Diplodocus might reflect different ecological niches and evolutionary trade-offs, further reminding us that dinosaurian superpowers were not a one-size-fits-all solution, but a diverse suite of adaptations tailored to specific environmental contexts. This fascination with the sauropod superneck underscores a broader theme in evolution. Sometimes, power comes not from deadly claws or crushing jaws, but from the ability to adapt form and function to exploit resources in innovative ways. Camarasaurus's graceful yet imposing neck exemplifies this principle, symbolizing the incredible biological ingenuity that allowed sauropods to become some of the longest-living and most successful dinosaurs of their era. As we continue our exploration, the next chapter invites us to consider another iconic dinosaur whose adaptations inspire awe: Stegosaurus. From towering supernecks to formidable weaponized tails, the Mesozoic world is rich with evolutionary marvels, each a vivid testament to the power and diversity of prehistoric life. Among the most instantly recognizable dinosaurs, Stegosaurus embodies the marriage of form and function through its distinctive shields and spikes, a testament to defense perfected by evolutionary pressure. In an era filled with predatory giants and fierce competition, Stegosaurus carved out its own survival superpower, not with speed or stealth, but with an arsenal of natural weapons combined with remarkable defensive intelligence. Stegosaurus lived during the Late Jurassic period, roughly 155 to 150 million years ago, roaming what is now North America. Measuring up to 9 meters in length and weighing around 5 tons, this quadrupedal herbivore was no lightweight. Yet, with its relatively small brain-to-body ratio, it might be easy to underestimate its ability to effectively defend itself. However, sparse though the cranial anatomy might suggest, numerous indications point toward a creature well adapted for protection, equipped both with formidable physical weaponry and strategic behaviors. The Stegosaurus's most famous defensive features were its large double row of upright plates running along its back, and its tail, a formidable weapon known as the thagomizer. The plates, varying in size and shaped somewhat like kite sails, are hypothesized to have served multiple functions: thermoregulation by dissipating heat, visual display for communication within species, or intimidation of rivals, and possibly even as a defense mechanism by making the dinosaur appear larger and more threatening. Though they were not weapons themselves, these plates formed a psychological front line, warning predators to think twice. By contrast, the tail of Stegosaurus was the epitome of a physical weapon. Its thagomizer consisted of 4 to 10 long pointed spikes arranged in a fan-like shape. This spiked tail could be swung with immense force, capable of inflicting serious, even lethal injuries to attacking predators. Biomechanical modeling estimates suggest that the tail swung from powerful musculature and flexible vertebrae could strike an adversary with the impact of a strong, deliberate blow. Fossil evidence provides fascinating corroboration. Injuries found in the ribs of predatory dinosaurs, matching the shape and damage pattern, suggest successful defensive strikes from Stegosaurus tails. The strategic use of this weaponry implies behavioral sophistication. Despite the modest brain size, about the size of a walnut relative to its body, Stegosaurus was not simply a passive target. The dinosaur likely exhibited calculated defense tactics, such as positioning itself to keep predators at bay using its tail, or herd behavior to collectively deter attacks. The flexibility and coordination required to wield this weapon effectively imply a degree of neural control and learning. Moreover, the tail's defensive capacity was enhanced by its structure. The vertebrae in the tail were reinforced with interlocking processes, providing strength and reducing the risk of injury during swings. Muscles anchored to these bones enabled rapid acceleration and powerful retraction of the tail, vital for delivering precise and forceful blows. Stegosaurus's defense system didn't rely solely on brute force. Its thick, armored skin provided a passive shield. Studies of fossilized skin impressions reveal a mosaic of small bony deposits, called osteoderms, distributed across the back and flanks. While less extensive than the osteoderm armor of ankylosaurs, this bony skin likely functioned as a deterrent and protection against bites or slashes. Interestingly, Stegosaurus might also have used sensory superpowers to augment its defense. Recent hypotheses propose that it possessed a so-called second brain in the spinal cord near the hips, a complex neural cluster that controlled locomotion and reflexes. This would have been crucial for the quick coordination of tail movement and stance adjustments during a threat, compensating for the limitations of its true brain size. Behaviorally, Stegosaurus may have used visual and auditory signals in defense and communication. Vibrations conveyed through the tail or ground, combined with the imposing sight of its plates and tail spikes, would send unmistakable warnings to predators or rivals. Such multimodal defense strategies emphasize that survival is a synergy of anatomy and behavior. Stegosaurus's superpowers echo through the evolutionary story as a striking example of how prey species can evolve complex mechanisms to thrive amidst pressing threats. It underscores a recurring theme in prehistoric life. Power is multifaceted, often encoded in the interplay of weaponry, defense, and intelligence. As we continue our exploration into dinosaurian superpowers, the following chapter will unveil the social dynamics of herding dinosaurs, revealing the invisible threads of camaraderie and cooperation that further amplified survival and conquest in the ancient world. From weaponized tales to complex social behavior, the saga of dinosaurs is a rich tapestry of life's incredible adaptations. In the vast prehistoric landscapes where towering predators and colossal herbivores coexisted, survival was often more than an individual endeavor. It was a collective dance of social interaction and cooperation. Among the myriad superpowers evolved by dinosaurs, the ability to form cohesive groups or herds stands out as a profound evolutionary adaptation. The social superpowers of herding dinosaurs not only enhanced their defense and foraging efficiency, but also reshaped their behavior, communication, and even evolutionary trajectories. This chapter takes us deep into the complex world of dinosaur sociality, unraveling how camaraderie became a vital superpower in the Mesozoic era's unforgiving theater. Herding behavior is most extensively documented among herbivorous dinosaurs, particularly within groups like ceratopsians, hadrosaurs, and sauropods. Fossil evidence provides compelling snapshots of communal living: massive bone beds containing hundreds of individuals, trackways evidencing synchronized movement, and even nesting sites suggesting coordinated reproductive strategies. These clues paint a vivid picture of social networks that extended from juvenile groups to vast multi-generational herds. One of the primary advantages of herding was defense. In a world teeming with predators such as tyrannosaurs, allosaurs, and dromaeosaurs, being part of a group significantly reduced individual vulnerability. The classic safety in numbers enhanced vigilance, where multiple eyes could detect threats early and collective reactions could thwart attacks. Large herds could also confuse or intimidate predators simply by their sheer number and coordinated movements. Among sauropods, for instance, evidence from trackways shows them moving in organized groups along the same paths, perhaps migrating to optimal feeding grounds or watering holes. Their enormous size combined with herd dynamics transformed them into daunting challenges for any predator. Similarly, ceratopsians like triceratops exhibit patterns indicating group behaviors, with fossilized remains found together, hinting at social structures in both feeding and protective contexts. Beyond protection, herding facilitated more efficient foraging. Dinosaurs often inhabited varied and sometimes scarce environments. Coordinated movement allowed herds to exploit patchy vegetation more systematically, reducing overgrazing and promoting sustainable feeding. Young or weaker individuals could benefit from adult protection while learning feeding routes and behaviors, essentially passing down vital survival knowledge through generations. The social superpower extended into reproductive strategies. Nesting grounds showing high-density egg clutches from hadrosaurs and other herbivores indicate communal nesting, where individuals laid eggs in proximity. This behavior likely offered protection to the vulnerable young during early development stages. Additionally, evidence suggests some dinosaurs engaged in parental care, further reinforcing group cohesion and survival prospects. Communication within these herding societies was critical. While direct evidence is scarce, anatomical structures such as crests, frills, and other display features point towards visual signaling both within and between groups. Vocal communications, inferred from similarities with modern birds and reptiles, likely played roles in warning calls, mating calls, or maintaining group cohesion. The resonance chambers in certain skulls and the possibility of specialized vocal organs reveal a complex auditory landscape facilitating social interaction. The cognitive demands of herd living also hint at advanced neurological capacities. Navigating social hierarchies, coordinating defense, and engaging in cooperative behaviors require memory, recognition, and learning. While dinosaurs varied widely in brain size and complexity, the neurological capabilities necessary for these interactions were undoubtedly present in many species, laying grounds for the evolution of increasingly sophisticated social behaviors. Fascinatingly, herding behavior also shaped evolutionary paths by influencing traits favored by natural selection. Features enhancing group communication, such as bright coloration, elaborate frills, or synchronized movements, became selected traits, intertwining sociality with physical evolution. This confluence illustrates how biological superpowers often encompass not just raw physical traits, but also social intelligence and cooperative strategies. In carnivorous dinosaurs, hunting in packs or coordinated groups is a debated topic, but carries intriguing implications. Some dromaeosaurs, like those related to Velociraptor, may have collaborated during hunts, combining agility and coordination to take down prey larger than themselves. If true, this behavior would have amplified their hunting efficiency, a formidable example of social superpower among predators. In summary, the social superpowers of herding dinosaurs embody a multifaceted evolutionary triumph, where cooperation and camaraderie became as vital as size, strength, or weaponry. These ancient communities navigated perilous worlds with collective resilience, demonstrating that in the story of life, social connection magnifies survival. As we transition to the next chapter focusing on Microraptor and the first feathered flyers, we see that superpowers also took to the skies, expanding the boundaries of dinosaurian abilities. From sprawling herds on land to delicate wings in the air, the saga of dinosaur evolution is a rich chronicle of extraordinary adaptations shaped by the relentless forces of nature. In the shadowed forests of the early Cretaceous period, approximately 120 million years ago, a remarkable evolutionary spectacle unfolded that would alter the course of life on Earth. The rise of the first feathered flyers. Among these pioneering creatures, Microraptor, a small, agile dinosaur with a dazzling array of feathers not just on its arms, but also on its legs and tail, stands as a quintessential icon of this transformative chapter. As we explore Microraptor and the origins of avian flight, we delve into the evolutionary innovations that launched the dynamic journey from terrestrial dinosaur to aerial bird. Microraptor, meaning small thief, measured roughly the size of a crow, with a lightweight body adapted for agility and maneuverability. Discovered primarily in the fossil-rich Liaoning province of China, its well-preserved specimens astonished paleontologists with intricate feather impressions, revealing 4 wing-like surfaces, forelimbs, hind limbs, and a feathered tail. This unique morphology suggests an intermediate mode of flight between gliding and powered flight, offering significant insight into the evolutionary steps toward sustained aerial locomotion. Feathers, a hallmark trait long associated with modern birds, had deep evolutionary roots extending before true birds emerged. Initially believed to be exclusive to avian species, fossils over the past few decades have unequivocally demonstrated that feathers first evolved in various non-avian theropod dinosaurs, including Microraptor and its close relatives. These feathers likely began as simple filamentous structures, perhaps serving as insulation or for display, later evolving complex veins and aerodynamic forms conducive to flight. Microraptor's feather arrangement exemplifies this evolutionary sophistication. Its forelimbs bore primaries and secondaries analogous to modern bird wings, providing the primary lift surfaces. The hind limbs, equipped with similarly well-developed flight feathers, functioned as additional airfoils, facilitating enhanced control and stability during gliding or flapping. The feathered tail acted as a rudder, aiding in navigation and balance during aerial maneuvers. The presence of 4 distinct wings marks an evolutionary experiment in locomotion unparalleled among both extinct and extant species. Microraptor likely employed an arboreal lifestyle, launching from tree branches and using its wings to glide between trees or descend to the ground, an adaptation that granted it access to new ecological niches, including hunting insects, small vertebrates, or scavenging opportunities. This suggests that powered flight did not emerge abruptly, but rather through incremental stages, from simple feather-like structures aiding in insulation and display, to gliding and parachuting locomotion, culminating in the development of flapping flight as seen in later avian species. Microraptor epitomizes a critical transitional form in this continuum, bridging winged dinosaurs and true birds. Additionally, Microraptor possessed anatomical features enhancing its aerial capabilities. Its furcula, or wishbone, a bone critical to the flight mechanism in modern birds, was well developed, suggesting the musculature necessary for flapping. The skeletal frame was lightweight, with hollow bones reducing mass without sacrificing strength, a pre-adaptation vital for flight. The respiratory system of Microraptor, inferred from related theropods, likely featured air sacs similar to modern birds. These air sacs enhance oxygen exchange efficiency, support high metabolic rates, and reduce body weight, further hinting at the energetic demands and physiological sophistication required for aerial activity. Microraptor's feather coloration and patterns offer another fascinating dimension. Some fossil evidence suggests iridescent or patterned plumage, perhaps serving roles in camouflage, intraspecies communication, or sexual selection. This behavioral complexity complements its physical adaptations, highlighting the multifaceted nature of early avian superpowers. While Microraptor and its kin represent nature's early avian experiments, their story is part of a broader narrative in which the transition to flight was a mosaic of evolutionary innovations. It reminds us that evolutionary advancements often arise through a patchwork of traits gradually coalescing into new capabilities, rather than sudden leaps. The legacy of Microraptor reaches far beyond its early Cretaceous forest habitats. Its features laid the groundwork for the explosion of avian diversity following the mass extinction at the end of the Cretaceous, ultimately giving rise to the birds that dominate our skies today. This remarkable journey from feathered gliders to masterful flyers eloquently illustrates life's boundless capacity for innovation. Moving forward from these first feathered flyers, our exploration will take us to the open plains, where speed demons like the ornithomimids showcased dinosaur superpowers of sprinting and agility. A different yet equally captivating chapter in the evolution of prehistoric adaptation. Among the most fascinating and dynamic dinosaur superpowers was the evolutionary mastery of speed and agility, embodied spectacularly by the ornithomimids, often likened to the ostrich dinosaurs of the Mesozoic. These swift, graceful beings weren't just fleet-footed. They represented a profound leap in locomotive evolution, poised as some of the fastest creatures of their era, masters of the art of prehistoric sprinting. Their anatomical innovations and ecological niches showcase how speed itself became a formidable survival and predatory strategy, highlighting an alternative form of power reliant on movement and endurance, rather than brute force. Ornithomimids flourished primarily during the Late Cretaceous period, approximately 95 to 66 million years ago, and their fossils have been found across North America and Asia. Ranging in size from about 3 to 4 meters long, these dinosaurs possessed lean, lightweight bodies optimized for rapid locomotion. Unlike the bulky and heavily armored herbivores or the robust, heavy-set carnivores, ornithomimids displayed an exquisite blend of anatomical traits specifically adapted for speed and maneuverability. The foundation of their sprinting prowess lay foremost in their skeletal structure. Long, slender hind limbs with elongated lower segments, particularly the tibia and metatarsals, functioned much like the long legs of modern cursorial animals. Combined with a digitigrade stance, where the animal stood on its toes much like a running bird or a horse, this design enhanced stride length and cadence, critical parameters for achieving high speeds over varying terrains. Adding to this, the ornithomimid pelvis and tail configuration contributed to balance and agility. A strong, muscular tail acted as a counterbalance, stabilizing rapid turns and sudden accelerations. Their tails were flexible, yet sturdy, enabling quick directional changes while maintaining momentum, vital for escaping predators or pursuing elusive prey. Their overall body plan was streamlined with reduced weight. Lightly built skulls with small teeth or no teeth at all evolved in certain species toward a beak-like mouth, suited for omnivory or herbivory, rather than heavy biting. This reduction not only minimized cranial mass, but contributed to overall aerobic efficiency, allowing for sustained high-speed movement without incurring excessive metabolic costs. Moreover, the ornithomimid forelimbs were relatively long and equipped with grasping hands, providing a multifunctional limb capable of handling food, aiding in balance, and perhaps even helping to stabilize during rapid movement. Combined, these features created a remarkably versatile and well-integrated locomotor system. The lung and respiratory systems of ornithomimids, while indirectly studied through comparisons with modern birds and related theropods, likely featured advanced air sacs and a flow-through lung mechanism. This respiratory efficiency enabled quicker oxygen uptake and delivery to muscles, essential for powering bursts of speed and maintaining stamina, particularly useful in predator evasion or foraging over wide areas. Trackway evidence yields insights into the actual performance of these dinosaurs. Fossilized footprints demonstrate stride lengths and pacing consistent with rapid running. Moreover, these tracks sometimes exhibit evidence of herding behavior, suggesting that ornithomimids may have relied on social cooperation while moving swiftly across Mesozoic plains and forests. Ecologically, speed provided ornithomimids with multiple advantages. Their diet likely included plants, small animals, insects, and perhaps scavenged remains, demanding the capacity to cover wide ranges to exploit scattered resources. High locomotor endurance paired with quick bursts of speed helped them escape threats from larger predators, who, despite their size and power, may have struggled to match the ornithomimid's agility. Interestingly, Recent discoveries show evidence of feathers or feather-like coverings on these dinosaurs, which could have served dual purposes: insulation and aerodynamics. Feathers may have contributed to reducing drag and improving stability during rapid movement, much like the contour feathers of modern birds aid in flight and sprinting. Behaviorally, speed was not merely a defense or foraging asset, but may have played a role in mating rituals and territory defense. Quick movements, elaborate displays aided by feathers, and vocalizations might have been integrated into complex social interactions where agility translated into evolutionary fitness. In summary, ornithomimids stand as exemplars of evolution's pursuit of speed as a survival superpower. Their anatomical, physiological, and behavioral attributes created a dinosaur that combined grace, endurance, and rapidity, reshaping the predator-prey dynamics and ecological frameworks of their time. They remind us that power in the prehistoric world was multifaceted, sometimes measured in strength or size, other times in sheer, breathtaking velocity. Next, our journey will delve into the subtle and fascinating thermoregulatory tricks dinosaurs employed, involving insulation, color variation, and feathers, revealing yet another layer of their evolutionary ingenuity. From sprinting across ancient landscapes to coloring the prehistoric palette, the world of dinosaur superpowers continues to astonish. The sun bore down relentlessly on the ancient landscapes of the Mesozoic era, where dinosaurs thrived amid dramatically shifting climates and diverse environments. In this world, managing body temperature was a vital, life-sustaining superpower. Unlike modern mammals and birds, whose warm-blooded metabolisms generate consistent internal heat, dinosaurian thermoregulation remains one of paleontology's most captivating and complex mysteries. Yet, evidence increasingly reveals that dinosaurs employed ingenious physiological and behavioral strategies involving insulation, color modulation, and feathers to maintain optimal body temperatures, adaptations that echo profoundly in their evolutionary legacy. Thermoregulation, the ability to keep one's body temperature within a certain range, is essential for all animals. In dinosaurs, a spectrum of thermoregulatory mechanisms likely existed, tailored to their size, habitat, and metabolic capabilities. Large sauropods, with their colossal mass, benefited from inertial homeothermy, maintaining stable internal temperatures simply due to their volume. Smaller dinosaurs, however, faced greater challenges losing heat more rapidly and therefore needed insulative adaptations. Feathers, now famed for their role in avian flight, originally evolved as one of these crucial thermoregulatory tools. The earliest feathers, seen in basal theropods and some ornithischians, were simple filamentous structures, much like down feathers on modern birds, providing insulation. This delicate layer would reduce heat loss in colder conditions and shield against excessive heat by reflecting sunlight or facilitating evaporative cooling. Fossil evidence from the Liaoning province of China, highlighting species like Sinosauropteryx and Caudipteryx, showcases well-preserved melanosomes, microscopic pigment-containing organelles, within feather impressions. These discoveries enable scientists to infer coloration patterns and suggest that feathers' color also contributed to temperature regulation. Light-colored feathers may have reflected more solar radiation, keeping dinosaurs cooler in exposed areas, while darker hues absorbed heat in cooler climates or seasons. Beyond color, feather placement and morphology played a functional role. Dense feathering in key regions such as the neck, chest, and tail would have been vital for heat retention. The mobility of these feathers, possibly erecting or flattening them in response to temperature changes, provided dynamic insulation. Such mechanisms resemble modern birds and mammals, raising fur or feathers to trap heat, or flattening them to dissipate it. In addition to insulation, behavioral thermoregulation was likely widespread among dinosaurs. Like reptiles and birds today, dinosaurs might have basked in the sun to warm up after cool nights, or sought shade or water to cool down. The arrangement of their feathering and skin color patterns would amplify these behaviors. Seasonal or even daily changes in hue could modify heat gain or loss. Skin color patterns, inferred through pigment studies in fossilized keratin or melanosomes, suggest some dinosaurs possessed cryptic coloration for camouflage, while others may have displayed vibrant colors for signaling or sexual display. These colorful displays could also have thermoregulatory effects, balancing the need to attract mates or deter rivals with survival demands. Remarkably, some speculations also propose that the sail-like structures seen in species such as Spinosaurus or neural spines in certain ornithischians might have aided in thermoregulation by increasing surface area to dissipate or absorb heat. Though functions like display or fat storage have been suggested, the thermoregulatory hypothesis remains plausible given their vascularization and positioning. The presence of feathers and skin pigment adaptations also suggests that dinosaurs had already evolved complex internal mechanisms to regulate their metabolic processes, supporting the theory of at least partially warm-blooded metabolisms in many dinosaur lineages. Such metabolic rates require efficient heat management strategies, reinforcing the importance of insulation and coloration. In summary, thermoregulation in dinosaurs was a multi-layered, dynamic superpower involving physical insulation via feathers and skin, color modulation through pigmentation, and sophisticated behavioral adaptations. These characteristics combined to help dinosaurs thrive across varying climates, elevating their ecological versatility and resilience. The evolutionary innovations in dinosaur thermoregulation opened pathways for survival in diverse habitats and set the stage for the development of modern birds' finely tuned insulating feathers and color-based communication. As we journey forward, the next chapter will unravel the intriguing metabolic mysteries of dinosaurs, the ongoing debate among scientists about warm-bloodedness, cold-bloodedness, and fascinating hybrid states that these magnificent creatures might have exemplified. This exploration will deepen our understanding of how life's internal dynamics powered some of the most extraordinary creatures ever to walk the earth. Exploring the metabolic nature of dinosaurs invites us into one of the most profound and ongoing debates in paleontology. Were dinosaurs warm-blooded like modern birds and mammals, cold-blooded like many reptiles, or something in between? A hybrid metabolic state, exhibiting superpowers of both. This question strikes at the heart of how dinosaurs lived, moved, and thrived for over 160 million years, shaping their biology and ecology in ways that still captivate scientists today. Metabolism refers to how organisms convert food into energy and regulate their internal body temperature. Warm-blooded animals, or endotherms, generate heat internally to maintain a stable body temperature regardless of the external environment, supporting sustained activity and complex behaviors. Cold-blooded animals, or ectotherms, rely largely on ambient temperatures to regulate their body heat, often resulting in periods of low activity and dependence on environmental conditions. Traditionally, dinosaurs were thought to be cold-blooded reptiles, sluggish in cooler conditions. However, accumulating evidence challenges this notion. Many dinosaurs show anatomical and physiological features indicating higher activity levels and metabolic rates than typical ectotherms. One compelling line of evidence is bone histology. Microscopic examination of dinosaur bones reveals growth patterns and vascularization indicating rapid growth rates consistent with endothermy, or at least an intermediate metabolic rate. Some small theropods show especially fast growth and dense bone vascularization similar to modern birds. Respiratory anatomy also supports elevated metabolism. The presence of air sacs and a bird-like lung system in many theropods suggests efficient oxygen exchange and high metabolic capacity necessary for sustained activity and thermoregulation. Furthermore, feathers, not only for display and flight, likely played a role in insulation, indicating thermoregulatory adaptations associated with warm-bloodedness. Insulating feathers would be less beneficial for cold-blooded creatures. On the behavioral side, fossilized trackways exhibit continuous movement and migration in herd animals, suggesting endurance and active lifestyles inconsistent with ectothermic patterns. Despite this, the enormous sizes of some sauropods present physiological puzzles. Sustaining a high metabolic rate would require vast quantities of food. Some scientists hypothesize that such giants used gigantothermy, leveraging massive body size to retain heat passively, which offered a hybrid form of thermoregulation without the extreme energetic demands of a fully endothermic metabolism. Likewise, some smaller dinosaurs may have been fully warm-blooded, others cold-blooded, and many occupying intermediate niches, a metabolic spectrum shaped by ecological niches, climate, and evolutionary pressures. This heterogeneity underscores that evolutionary strategies are rarely black and white. Recent isotope analyses from fossil bones add to this complex picture, revealing variations in body temperatures and feeding ecologies indicative of dynamic metabolic adaptations. In sum, dinosaurs likely exhibited a range of metabolic strategies, ranging from warm-blooded to cold-blooded, with many species displaying hybrid or novel thermoregulatory mechanisms, superpowers that allowed them to exploit diverse environments and lifestyles. This metabolic diversity contributed profoundly to their evolutionary success, enabling dinosaurs to be fast predators, massive herbivores, and master survivors. As we move forward, the forthcoming chapter delves into the fascinating world of dinosaur communication, exploring their hidden language of display, courtship, and social interaction, expanding our understanding beyond physiology into behavior and intelligence. The metabolic foundations laid here underpin those miraculous social and survival strategies that made dinosaurs legends of the prehistoric world. Throughout the vast and varied landscapes of the Mesozoic era, dinosaurs communicated in ways as rich and complex as their physical adaptations. Beyond the roars, snarls, and movements readily imagined by many, these ancient creatures developed a hidden language, a symphony of displays, vocalizations, visual signals, and behaviors that facilitated communication, territoriality, mating, and social cohesion. This intricate tapestry of signals represents yet another evolutionary superpower, one woven from the nuances of perception and interaction, illuminating the sophisticated social lives of dinosaurs. Visual display was paramount among dinosaurs as a mechanism to convey messages over distances and through the dense foliage that many inhabited. Many species bore elaborate crests, frills, horns, and plates, each structure evolving as a biological billboard. Take, for instance, the ceratopsians, whose extravagant frills and horns not only served defensive purposes, but likely acted as displays of fitness, species identity, and social status. The variation in shape, size, and ornamentation within species hints at sexual dimorphism and the signaling of reproductive readiness. Similarly, the majestic plates of Stegosaurus, with their broad surfaces and possible vascularization, may have been employed in visual signaling. Their ability to change posture alongside the presumed colorful keratin sheaths covering these plates could provide flashing displays to warn rivals or attract mates. Beyond static structures, dynamic behaviors such as posturing and movement intensified these visual cues. Tail swishing, head bobbing, or crest flaring might have served as ritualized communication or deterrence. Vocal communication, while more challenging to study due to the fragility of soft tissues, likely played a critical role. Anatomical evidence, such as peculiar features found on the bones of the larynx or specialized structures within nasal cavities, suggest some dinosaurs produced low-frequency sounds capable of traveling long distances, similar to the infrasound used by modern elephants and whales. These sounds could have been integral for group coordination, territorial claims, or courtship calls, deepening social bonds or deterring rivals. Certain hadrosaurs, known as the duck-billed dinosaurs, possessed elaborate crests with complex nasal passages. These crests might have functioned as resonating chambers, creating distinctive sounds. The diversity of crest shapes across hadrosaur species and individuals implies species-specific calls, a necklace of acoustical identity essential for communication within mixed-species communities. The role of color and patterning in dinosaur communication is another fascinating dimension illuminated through fossil melanosome analysis. Feathers and skin pigmentation in many theropods display iridescence, stripes, spots, or bold contrasting colors. These patterns would have played a pivotal role in visual signaling for mate attraction, species recognition, or camouflage. Imagine a microraptor gleaming with iridescent feathers maneuvering deftly through dappled forest light, communicating dominance, courting mates, or evading predators through a choreography of color and motion. Touch and tactile communication also likely played roles, especially within social or parental contexts. Physical greetings, nuzzling, or the deliberate touching of mates could foster bonding and reinforce social hierarchies. Such behaviors parallel those seen in modern birds and reptiles and are critical for complex social structures. Courtship itself was a stage for intricate display interactions. From the elaborate dances of some theropods to the showcasing of vibrant plumage or foot stomping, courtship displays were vital evolutionary superpowers that enhanced reproductive success. These rituals assured mate quality and species compatibility, driving sexual selection and influencing evolutionary trajectories. Moreover, the evolution of the brain and sensory organs in dinosaurs supported processing these complex signals. Enlarged regions dedicated to vision, hearing, and smell enabled rapid perception and response to social cues, allowing swift behavioral adaptations crucial for survival and reproduction. The hidden language of dinosaurs thus emerges as a mosaic of visual artistry, acoustic sophistication, chemical signaling, and tactile interaction. Its richness challenges us to think beyond the brute force of prehistoric life and envision a world vibrant with social complexity, emotional nuance, and communication networks that shaped the success of these ancient titans. As we progress deeper into the saga of dinosaurian superpowers, the next chapter will pit two of the largest predators, Giganotosaurus and Tyrannosaurus rex, against each other, exploring their distinct evolutionary advantages and what made them the formidable kings of their domains. This confrontation of monstrous power and cunning echoes the interplay of physical might and behavioral brilliance we've seen woven through dinosaur history. In the annals of prehistoric giants, few rivalries capture the imagination as vividly as the titanic clash between Giganotosaurus carolini and Tyrannosaurus rex, two of the most formidable theropod dinosaurs to have ever stalked the Earth. Although these colossal predators lived millions of years apart and on different continents, their evolutionary parallelism and sheer power invite comparisons that illuminate distinct paths to apex predation. Understanding the unique superpowers of these Jurassic and Cretaceous kings reveals the intricacies of their anatomical design, hunting strategies, and ecological dominance. painting a mesmerizing picture of rivalry etched by evolution itself. Giganotosaurus, meaning giant southern lizard, roamed what is now South America approximately 98 million years ago during the Late Cretaceous. Estimated at around 12 to 13 meters in length and tipping the scales up to 8 tons, it is among the largest terrestrial carnivores ever discovered. Its robust build, extensive skull length, measuring nearly 1.8 meters, and massive jaws signal a predator engineered for power and precision. Tyrannosaurus rex, the tyrant lizard king, emerged in North America some 66 million years ago, around 30 million years after Giganotosaurus had vanished. Slightly shorter but bulkier, T-Rex stretched 12 meters long and could weigh upwards of 9 tons. Its skull was extraordinary, with a more rounded snout and reinforced bone structures capable of exerting unparalleled bite force. One of the most striking differences lies in their bite mechanics and dental adaptations. T-Rex possessed enormous, thick, and robust teeth designed to crush bone, enabled by the strongest bite force of any known terrestrial animal, estimates reaching over 35,000 newtons. This bone-crushing ability allowed T-Rex to access marrow and thoroughly dismantle carcasses, making it an efficient hunter and scavenger. The teeth's serrated edges acted like blades slicing through muscle, but packed the power to break dense bone. Giganotosaurus, by contrast, wielded sharper, more blade-like teeth suited for slicing flesh rather than crushing bone. Its jaws, though powerful, were adapted for delivering slashing bites that could inflict deep, bleeding wounds quickly to incapacitate prey. The lighter skull architecture facilitated faster jaw movement, favoring rapid slashing over sheer crushing power. This methodology suggests Giganotosaurus preyed on massive sauropods and other large herbivores by wounding and weakening them rather than pulverizing bones outright. Locomotory differences also reveal nuanced tactical advantages. Giganotosaurus, with its relatively longer and more gracile limbs, may have been faster and more agile than T-Rex, adapted for pursuit and active hunting in open environments. Tyrannosaurus rex, on the other hand, had a more robust yet powerful build, possibly favoring ambush predation and overpowering prey at close quarters. These adaptations reflect their respective ecosystems. Giganotosaurus hunted in vast floodplains with herds of daunting sauropods like Argentinosaurus, requiring speed and slashing effectiveness to tackle gargantuan prey. Tyrannosaurus rex lived alongside large, robust herbivores like Triceratops and Edmontosaurus, which could be dispatched with crushing bites and overwhelming force. Sensory capabilities also distinguished these predators. Studies of T-Rex brain cases reveal a highly developed olfactory bulb, indicating an extraordinary sense of smell, potentially aiding in hunting, scavenging, and social behavior. Its vision was stereoscopic and acute, ideal for detecting movement and depth. Giganotosaurus likely shared some sensory superpowers, but may have relied more on vision and agility than the remarkable olfactory acuity of T-Rex. Social behavior, although still under study, might have varied. Some evidence suggests that Giganotosaurus could have hunted in groups or packs, coordinating attacks on massive prey, while T-Rex is often thought to be more solitary, relying on individual strength and territorial dominance. Ultimately, comparing Giganotosaurus and T-Rex highlights two distinct evolutionary strategies among apex predators, one emphasizing speed, slicing power, and possibly social cooperation, the other bone-crushing bite force, raw strength, and sensory acuity. Both were apex super predators of their time, dominating their landscapes through complementary adaptations honed by millions of years of evolution. As we conclude this confrontation of prehistoric titans, our exploration will next shift focus to the intimate realm of parental care in dinosaurs. another remarkable suite of superpowers ensuring survival and continuity. From brutal battles of giants to tender bonds of nurture, the narrative of dinosaurs continues to fascinate and inspire. The story of dinosaurs is not solely one of immense size, devastating weaponry, or spectacular adaptations for survival. It is also a tale of care, nurturing, and intricate family bonds. Parental care stands as a profound superpower among many dinosaur species, showcasing their intelligence, social complexity, and commitment to their offspring's survival. Far beyond the archaic image of cold, indifferent reptiles, dinosaurs exhibited behaviors strikingly reminiscent of modern birds and mammals, leaving a legacy of nurturing that connects the ancient world to the present day. Evidence for parental care among dinosaurs comes from a multidisciplinary blend of fossilized nests, embryonic remains, growth studies, and trace fossils. Among the most compelling finds are the meticulously preserved nesting sites, with clusters of eggs arranged in patterns, suggesting careful construction and repeated use. Hadrosaurs, ceratopsians, oviraptorosaurs, and some theropods are well-documented examples that constructed nests, incubated clutches, and even guarded their young. Oviraptorosaurs provide a quintessential example. Long thought to be egg thieves, new fossil finds revealed adult dinosaurs sitting atop nests in brooding postures remarkably similar to modern birds. This behavior implies active incubation, possibly involving temperature regulation through body contact. Such protection extended beyond mere incubation. Nesting sites show signs of communal care where multiple individuals might have cooperated to raise their young. Developmental studies of dinosaur embryos and juveniles reveal rapid growth rates indicative of sustained parental feeding and protection. Fossils of young dinosaurs found alongside adults suggest these juveniles stayed close to parents for extended periods, presumably for warmth, protection, and nourishment. This parallels parental care patterns seen in many birds today, where fledglings rely on parental resources until capable of independence. Tracking footprints and bone beds also offer glimpses into group dynamics. Juvenile trackways accompanying adult herds suggest family-oriented social structures, with parents guiding and safeguarding their offspring. This social cohesion would have enhanced survival odds in predator-rich environments. Parental care furnished evolutionary advantages beyond mere survival. By investing resources in fewer offspring with higher survival probabilities, dinosaurs optimized reproductive success. This nurturing approach may have driven the evolution of social behaviors, communication, and ultimately cognitive skills instrumental in the rise of complex dinosaurian societies. Moreover, the close behavioral parallels between nurturing behaviors in dinosaurs and birds illuminate the deep-rooted legacy of care across millions of years. Many of the physiological and anatomical traits facilitating parental care, such as feathers for brooding insulation and sophisticated vocal communication, arose well before avian birds, underscoring dinosaurs' role as evolutionary forerunners of modern nurturing strategies. Importantly, these superpowers of parental care also reflect dynamic adaptation to ecological pressures. In predator-dense or challenging environments, attentive care conferred decisive survival edges, embedding nurturing deeply within dinosaur life histories. Ultimately, recognizing dinosaurs as super nurturers enriches our understanding of their lives far beyond their formidable physical traits. It emphasizes the social and emotional complexities within these ancient creatures, forging a profound connection to the natural world we inhabit today. As we continue our journey through dinosaur superpowers, the next chapter will explore the astounding bone strength and sheer massiveness of Dreadnoughtus, giants built on a skeletal framework engineered for unbeatable mass and durability. From nurturing care to structural strength, The world of dinosaurs offers infinite marvels born from life's relentless evolutionary creativity. Among the giants that roamed our planet during the late Cretaceous period, one name stands out for its sheer mass and bone-crushing strength: Dreadnoughtus schrani, aptly named to evoke an image of unstoppable power akin to the legendary battleships of the early 20th century. This colossal titan, discovered in the Patagonia region of Argentina and dating back approximately 77 million years, redefines our understanding of vertebrate musculoskeletal engineering, exemplifying how evolution forged bodies capable of not only immense size, but also incredible structural integrity, the very foundation of dinosaurian superpowers. Dreadnoughtus is one of the largest land animals whose nearly complete skeleton has been unearthed, measuring an estimated 26 meters, about 85 feet, in length, and weighing an astonishing 59 metric tons or more. Its towering stature and massive dimensions prompt an essential question. How could any biological framework support such tremendous weight without collapsing under its own mass? The answer lies in the remarkable design of its bones and body structure. A defining feature of Dreadnoughtus is its robust and extraordinarily thick limb bones, particularly the femur and humerus, which are characterized by massive diameters and dense cortical bone tissue. These bones exhibit a unique combination of strength and resilience, designed to withstand enormous compressive and bending forces during locomotion and weight-bearing. The internal architecture is complex, featuring a lattice of trabecular bone, spongy, porous structures strategically oriented to absorb stress and distribute load efficiently throughout the skeleton. This bone density is not merely for bulk. It represents an evolutionary optimization balancing strength and weight. Unlike modern elephants, which possess dense but comparatively lighter limbs, Dreadnoughtus's heavy limb bones functioned as durable columns that supported its gargantuan body, preventing fractures and mechanical failure. This impressive skeletal fortification was essential given the enormous kinetic forces involved when the animal moved or rested. Moreover, its vertebral column reveals unique adaptations. The presacral vertebrae, forming the neck and back, contain extensive pneumatic cavities, air-filled spaces interconnected with the respiratory system. This pneumaticity reduced the overall skeletal weight while preserving rigidity and strength, a crucial evolutionary trade-off enabling the sauropod to maintain its elongated neck and massive torso without becoming unbearably heavy. The bones of Dreadnoughtus also display muscle attachment scars that indicate powerful musculature anchoring, contributing to the animal's capacity for movement despite its mass. Its limbs were stout, but articulated for supporting and moving such a colossal frame, at least with slow, steady locomotion, enabling access to vast feeding ranges and escape from predators or environmental threats. Fossilized bones show particular resistance to stress through their microstructure. Numerous osteons, the microscopic units of compact bone, are densely packed to resist cracking and fatigue. This feature was imperative for an animal whose bones bore repeated stress cycles over decades, an indication of longevity and durability. Comparative anatomy reveals that Dreadnoughtus's superpower of bone strength exceeds that of many of its sauropod relatives. Its evolutionary niche as a gigantic herbivore required not just extreme size for deterrence against predators, but also skeletal fortitude to navigate diverse terrains, migrate if necessary, and sustain prolonged feeding sessions. Aside from mechanical strength, the bone composition also had metabolic roles. Mineral storage within bones served as reservoirs during periods of stress or nutritional scarcity, highlighting an additional layer of physiological versatility innate to such giants. Understanding Dreadnoughtus's unprecedented mass and bone superstructure deepens our insight into the limits of vertebrate architecture, informing fields beyond paleontology including biomechanics, material science, and robotics, where nature's innovations inspire modern technology. As we transition from structural marvels to ecological adaptations, the subsequent chapter will explore how marginocephalian dinosaurs, a group encompassing ceratopsians and pachycephalosaurs, developed superpowers finely tuned for desert survival. From massive bones to environmental mastery, the saga of dinosaurian adaptations continues to astonish with its extraordinary diversity and evolutionary ingenuity. Marginocephalians represent a fascinating clade of herbivorous dinosaurs, renowned for their distinctive cranial ornamentations and remarkable adaptations that enabled survival in some of the most challenging environments of the late Cretaceous period, including arid and semi-arid desert regions. Comprised mainly of ceratopsians, such as Triceratops and pachycephalosaurs, or dome-headed dinosaurs, these dinosaurs developed a suite of specialized traits, or superpowers, that allowed them to thrive under harsh desert-like conditions, characterized by extreme temperatures, scarce water resources, and variable vegetation. Deserts pose formidable survival challenges to large terrestrial animals. Water conservation, thermoregulation, foraging efficiency, and protection against predators all become paramount. Marginocephalians, against this backdrop, evolved unique anatomical and behavioral adaptations that collectively underpinned their ecological success in these inhospitable terrains. One key superpower was their cranial morphology. The massive bony frills and horns of ceratopsians functioned not only as defensive weaponry against predators, but also likely played critical roles in thermoregulation. These frills were often vascularized, meaning rich blood vessel networks existed within the bone, possibly enabling heat dissipation in scorching desert climates by acting as radiators, similar to how modern elephants' large ears help regulate body temperature. This physiological feature would have been pivotal in preventing overheating during high daytime temperatures. Furthermore, the robust skulls and horn arrangements may have been integral in intraspecific communication and social dominance displays, which maintained herd structures that provided safety and efficiency in resource utilization. Herding behavior itself becomes an indispensable superpower for desert survival, as coordinated group movement allows exploitation of patchy water sources and vegetation, while minimizing individual exposure to predators. In addition to their defense and social adaptations, marginocephalians exhibited specialized dental and digestive features adapted to arid environments. Their teeth were well suited for processing tough, fibrous desert vegetation, including drought-resistant cycads, conifers, and angiosperms, which could survive with minimal water. The development of complex dental batteries allowed efficient grinding and breakdown of plant material, maximizing nutrient extraction from scarce and coarse food sources. Water conservation might have been augmented by physiological adaptations such as efficient kidneys and behavioral strategies like nocturnal activity patterns to avoid the punishing heat of midday. While direct fossil evidence for these soft tissue adaptations is limited, comparative studies with modern desert-dwelling reptiles and mammals, combined with ecological inference, support this hypothesis. In some pachycephalosaurs, the thickened skull domes may have served multiple functions beyond combat or display. These structures could help shield the brain against heat stress or assist in thermoregulation, adding another layer to the multifunctionality of their distinctive morphology. Marginocephalians also likely employed visual and perhaps even color-based signaling adapted for desert environments, where visibility fluctuates with sandstorms, shifting sun angles, and sparse vegetation. Their frills and domes could have been adorned with vibrant colors or patterns, aiding in species recognition, mating rituals, and deterrence of predators, vital functions in an open and exposed milieu. The ability to endure and flourish in desert habitats illustrates the remarkable evolutionary plasticity of marginocephalians. Their combination of robust defensive structures, physiological adaptations for heat and water management, dietary specialization, and sophisticated social behaviors signifies a comprehensive superpower suite honed for desert life. These adaptations not only highlight the intricate interplay between anatomy, behavior, and environment, but also speak to broader themes of resilience and innovation within dinosaurian evolution. By mastering harsh conditions that challenged many contemporaneous species, marginocephalians carved out ecological niches that ensured their persistence until the end of the Cretaceous. As we proceed, the next chapter will delve into the intriguing world of dinosaur symbiosis, a largely hidden dimension of Mesozoic ecosystems revealing how life thrived through interconnected relationships. From desert-hardy adaptations to cooperative survival strategies. The saga of dinosaurian superpowers continues to unfold in unexpected and extraordinary ways. In the sprawling ecosystems of the Mesozoic, where the ground trembled beneath the feet of titanic sauropods and the skies were dominated by pterosaurs, life among giants was a dance of intricate relationships and survival strategies. The immense size of many dinosaurs conferred considerable advantages: protection from predators, dominance over resources, and remarkable physical capabilities. But these monumental creatures also navigated the challenges of coexisting with equally large species and myriad other organisms. Symbiotic relationships and ingenious survival tactics emerged as essential superpowers, enabling dinosaurs to flourish in complex communities shaped by cooperation, competition, and environmental pressures. Symbiosis, the close and often long-term interaction between different biological species, plays a pivotal role in maintaining the balance in ecosystems. Though direct evidence of symbiotic relationships among dinosaurs is challenging due to the incomplete nature of the fossil record, a wealth of indirect evidence synthesized through paleoecology has revealed fascinating insights into how dinosaurs and their contemporaries coexisted and cooperated. One of the most profound examples is the mutualistic relationships dinosaurs likely shared with microorganisms and smaller fauna that helped sustain their enormous bodies. Large herbivorous dinosaurs, such as massive sauropods and ceratopsians, subsisted on vast amounts of plant matter, including tough-to-digest fibrous vegetation. To process this efficiently, they depended heavily on gut microbiota, specialized communities of bacteria and protozoans that fermented cellulose and other complex carbohydrates, enabling nutrient absorption. This internal symbiosis between giant digestive tracts and microorganisms was a vital biological superpower, allowing dinosaurs to convert otherwise indigestible plants into energy, thus supporting their gargantuan sizes. Beyond internal assistance, external symbiotic interactions likely abounded. Fossilized remains occasionally reveal smaller animals, insects, lizards, or even early mammals that might have rid their colossal hosts of parasites through grooming or scavenging. Such cleaning symbioses, akin to those seen today between crocodiles and cleaning fish or birds and large mammals, would have benefited both parties. The smaller animals gained food, while the giants enjoyed increased health and comfort. The physical environment shaped yet another set of survival tactics. Enormous dinosaurs likely shaped landscapes through their movement, feeding, and nesting behaviors, altering plant formations, soil compaction, and water distribution. These biosphere engineers created habitats that benefited multiple species, enhancing biodiversity and ecosystem resilience. For example, the dominant foraging by hadrosaurs and ceratopsians could encourage new plant growth and create open spaces that smaller animals exploited. Predatory dinosaurs, conversely, had complex relationships with their prey and competitors. Some evidence indicates that group hunting strategies or territorial behaviors might have evolved to optimize hunting success and resource defense. Coordinated hunting would have enabled even relatively smaller predators, like dromaeosaurs, to take down larger prey, showcasing behavioral superpowers of cooperation and planning. Niches carved out by physical or behavioral adaptations often reduced direct competition, enabling coexistence. Spinosaurus, with its aquatic specializations, coexisted alongside terrestrial predators, each exploiting different prey classes. Similarly, varying feeding heights and techniques among herbivores minimized overlap, with some browsing high vegetation and others grazing low, reducing resource strain. Reproductive behaviors added another layer of symbiotic interaction. Nesting colonies indicate dinosaurs shared breeding grounds, sometimes alongside other species, benefiting from collective defense against predators and possibly environmental buffering. Parental care, described in earlier chapters, fostered survival of offspring in these crowded and competitive conditions. Climate fluctuations and environmental stressors during the Mesozoic also pressured dinosaurs to develop flexible survival tactics. Migration, seasonal herd movements, and dietary flexibility emerged as responses to changing vegetation patterns and water availability, reflecting superpowers of adaptability and resilience. Each symbiotic and survival strategy intertwined with physiology and behavior, demonstrating the multidimensional nature of dinosaur superpowers. They were not solitary titans, but participants in vibrant, interactive ecosystems where success depended on more than physical might, on relationships, cooperation, and adaptation. This web of interdependence imparts profound lessons about life's complexity and resilience. It also sets the stage for the following chapter, exploring dinosaur regeneration, the remarkable capacity for wound healing and possibly limb regrowth, adding yet another dimension to these extraordinary prehistoric superpowers. In this remarkable epoch, life among giants was sustained by the delicate balance of interconnected forces, a testament to evolution's ingenuity and the enduring power of symbiosis. In the grand saga of dinosaurian life, one of the less visible yet profoundly impressive superpowers is their capacity for healing and regeneration, a biological resilience that speaks volumes about their survival strategies in a world fraught with danger. While dinosaurs are often celebrated for their formidable size, aggression, or speed, their ability to recover from injuries and wounds reveals an inner strength that contributed significantly to their evolutionary success. This chapter unravels the remarkable evidence of wound healing and explores the tantalizing possibility that some dinosaurs could regenerate lost limbs, a phenomenon that, if confirmed, would elevate our understanding of their biology to extraordinary heights. Fossilized bones provide the primary window into dinosaur healing capabilities. Paleontologists have uncovered numerous specimens bearing clear signs of healed fractures, infections, and even bone remodeling, phenomena that demonstrate active physiological responses to injury. For instance, healed broken ribs, vertebrae with signs of repair, and fractured limb bones fused with new growth indicate that dinosaurs survived significant trauma, adapting to injury while maintaining mobility. One particularly famous example is the hadrosaur Edmontosaurus, whose skeletons commonly reveal claw marks and bite wounds partially healed, suggesting survival after predator attacks. Similarly, theropods like Allosaurus have been found with healed jaw fractures and injuries on their limbs, testament to the robustness of their healing mechanisms. Recent advances in imaging technology, such as computed tomography, CT scanning, allow detailed examination of fossil microstructures, unveiling patterns congruent with modern bone healing processes. These studies confirm that dinosaurs repaired bone breaks through stages of inflammation, callus formation, and remodeling, analogous to the healing seen in mammals and birds today. Beyond healing, the possibility of limb regeneration, though more speculative, is captivating. Limb regeneration, the regrowth of an entire appendage, exists prominently among certain modern animals like salamanders and some reptiles. Reports of dinosaur fossils displaying abnormal skeletal features have prompted scientists to consider whether similar regenerative capacities occurred in extinct dinosaurs. For example, certain fossilized specimens show evidence of bone regrowth that deviates from simple repair. These anomalies might represent partial regrowth or remodeling after severe trauma. Questions remain whether these features signify regenerative abilities comparable to those in living regenerative species, or are the result of unique dinosaurian healing strategies. Understanding limb regeneration's evolutionary context leads us to modern birds and reptiles, the dinosaur lineage's living descendants, many of which possess varying degrees of regenerative ability, particularly in tails and toes. This connection hints at the ancient origin of regenerative mechanisms, possibly inherited from dinosaurian ancestors. The metabolic characteristics of dinosaurs also influence the plausibility of efficient regeneration. A metabolism supporting rapid growth and high activity levels would be conducive to complex regenerative processes, requiring substantial energy and cellular machinery. Moreover, the ecological pressures faced by dinosaurs, including frequent interspecies conflicts, environmental hazards, and predator-prey dynamics, would have selected strongly for individuals capable of recovering from injuries or regrowing lost parts, providing a decisive survival advantage. The study of dinosaur regeneration interweaves paleontology, developmental biology, and comparative anatomy, enriching our understanding of how life heals and adapts. Discovering that dinosaurs may have possessed such regenerative superpowers not only elevates their biological complexity, but also inspires modern scientific inquiry into tissue regeneration and healing. As we move forward in this exploration, we will encounter the ultimate test that challenged dinosaur resilience, the extinction events that reshaped Earth's biosphere. These cataclysms forced dinosaurs to confront their limits, setting the stage for the emergence of new life forms and the retention of dinosaurian superpowers in their avian descendants. The saga of dinosaur regeneration thus stands as a profound reminder of life's enduring capacity for renewal, resilience, and adaptation in the face of adversity. A biological superpower that transcends time, connecting past and present through the remarkable story of survival. Extinction events stand as nature's ultimate crucibles of survival, testing the limits of biological resilience and adaptability. Among these, the mass extinction at the end of the Cretaceous period, approximately 66 million years ago, marks one of the most profound chapters in dinosaurian history. A cataclysmic upheaval that challenged the very existence of the world's dominant terrestrial vertebrates. The story of these extinction events is not just one of demise, but also of remarkable endurance, showcasing the superpowers of resilience, adaptation, and transformation that defined dinosaurs and their legacy. The Cretaceous-Paleogene (KPG) extinction event, often linked to a colossal asteroid impact near present-day Chicxulub in the Yucatan Peninsula, unleashed environmental chaos on a planetary scale. The immediate consequences, massive wildfires, a nuclear winter scenario with darkness and plummeting temperatures, acid rain, and a breakdown in photosynthesis, drove rapid and severe ecological collapse. While many dinosaur lineages vanished, this event simultaneously set the stage for profound evolutionary change. Dinosaurian resilience manifested in various ways. Fossil records indicate that while non-avian dinosaurs suffered catastrophic losses, certain lineages exhibited traits that allowed survival or rapid adaptation in fluctuating environments. This selective resilience is evident in birds, the only dinosaur descendants to survive and diversify into the avian superpowers we see today. Prior to the KPG boundary, other extinction pulses tested dinosaur endurance, from volcanic activity to climatic shifts, each offering a glimpse into the evolutionary pressures shaping their adaptability. These earlier events forged physiological flexibility, varied reproductive strategies, and behavioral plasticity that were crucial in weathering environmental stress. Moreover, some dinosaur species possibly had broader dietary niches or habitat preferences, which buffered them against extinction pressures. For instance, omnivorous or smaller-sized species might have better withstood resource scarcity, demonstrating how ecological versatility functions as a survival superpower. The extinction events also catalyzed ecological opportunity. The void left by vanished species opened niches, leading to adaptive radiations in surviving groups, including mammals and birds. This turnover exemplifies resilience not just as survival, but as the capacity for rebirth and diversification. Studying geological and paleontological records reveals how recovery from extinction involves complex ecological succession, where pioneer species stabilize environments, followed by increasing complexity and diversity. Dinosaurs' evolutionary legacies thus illustrate resilience's role in both endings and new beginnings. Additionally, the geological evidence of impact ejecta, shocked quartz, tsunami deposits, and global iridium layers correlates with abrupt biotic changes, underscoring the magnitude of challenges faced by dinosaurs. Understanding their responses deepens insight into extinction theory and survival biology. Crucially, the ultimate survival of avian dinosaurs emphasizes that even amid devastating extinction, biological superpowers like rapid reproduction, flight, metabolic efficiency, and ecological flexibility allowed lineages to persist and thrive. The KPG extinction event, therefore, stands not just as a tale of loss, but as a testament to life's tenacity. Dinosaurs confronted the ultimate test, and through resilience and adaptation, their essence continues in today's birds, living monuments to evolutionary endurance. As we proceed, the next chapter will examine these survivors, the superpowers that live on in modern birds, and how ancient dinosaurian traits persist, innovate, and inspire life's ongoing journey on Earth. The saga of extinction and survival bequeaths invaluable lessons about power, adaptation, and the persistence of life across epochs. From the shadowed recesses of prehistoric epochs to the skies above us today, the lineage of dinosaurs lives on in the birds that have captured our fascination and filled our landscapes with vibrant life. Modern birds, with their spectacular displays of flight, complex behaviors, and physiological marvels, represent the living legacy of dinosaurian superpowers that have endured, evolved, and flourished over millions of years. This chapter unveils these enduring superpowers, revealing how birds embody the evolutionary brilliance of their dinosaur ancestors, translating ancient adaptations into the successes of the present day. The journey from fearsome terrestrial theropods to agile avians was a remarkable evolutionary transformation marked by gradual co-option and refinement of existing traits. Feathers, once primarily for insulation or display in non-avian dinosaurs, became central to flight, a defining superpower of birds. The aerodynamic structure of flight feathers, with intricate arrangements of barbs and barbules, enables the generation of lift and precise maneuverability. Beyond flight, modern birds retain skeletal innovations inherited from their dinosaurian predecessors. Hollow, pneumatized bones reduce weight without sacrificing strength, permitting efficient aerial locomotion. The furcula, or wishbone, acts like a spring to store and release energy during wing beats, an elegant adaptation rooted in theropod evolution. The fused clavicles, keeled sternum for powerful flight muscle attachment, and digitigrade stance reflect a continuum of evolutionary design optimizing flight performance. In addition to anatomical traits, avian metabolic strategies echo dinosaurian superpowers. Birds are endotherms with high metabolic rates, enabling sustained activity and rapid recovery, traits hypothesized in many theropod dinosaurs. Their respiratory system, featuring air sacs and unidirectional airflow, provides unparalleled oxygen exchange efficiency, supporting endurance and swift flight. Sensory abilities exemplify another line of dinosaurian inheritance. Birds possess exceptional vision, often including ultraviolet perception, crucial for foraging and communication, mirroring the keen eyesight found in predatory dinosaurs. Their hearing and olfactory capacities, though variable, support nuanced social interaction, environmental awareness, and survival instincts honed over evolutionary time. Behaviorally, birds continue the social superpowers of their ancestors. Complex courtship displays, vocal communication rich in variety and context, and cooperative breeding behaviors embody social intelligence deeply rooted in dinosaurian lineages. Tool use and problem-solving, observed in corvids and parrots, reveal cognitive capacities that suggest evolutionary trajectories beginning in Mesozoic times. Moreover, the reproductive strategies of birds, including nesting, brooding, and parental care, directly reflect dinosaurian behaviors evidenced by fossilized nests and brooding postures. The use of feathers for insulation in eggs and chicks exemplifies both physiological and behavioral continuity. Ecologically, birds have expanded and diversified into a dizzying array of niches: predators, scavengers, pollinators, and seed dispersers, showcasing adaptive versatility inherited from their ancestors. Their ability to colonize deserts, forests, mountains, and urban environments today is a testament to this evolutionary legacy. Genetic and molecular studies corroborate these connections. DNA analyses position birds firmly within the theropod branch of the dinosaur family tree, elucidating shared developmental pathways and regulatory genes responsible for key traits like feather development and skeletal morphology. In essence, modern birds serve as living museums of dinosaurian superpowers, a testament to endurance and transformation that connects the ancient past with the vibrant present. Their diverse forms and extraordinary capabilities exemplify how evolutionary innovation enables life to persist and adapt through deep time. As we turn our gaze to the broader impact of these ancient superpowers, the next chapter explores the legacy of dinosaurian traits in today's creatures, revealing how the echoes of prehistoric adaptation continue shaping life across the globe. The story of surviving superpowers is not confined to birds alone, but resonates throughout the tree of life, inspiring wonder and scientific discovery. The incredible story of dinosaurs did not end with their extinction millions of years ago. Rather, it transformed, finding new expression and survival through the myriad creatures that inhabit our world today. The legacy of dinosaurian superpowers lives on, intricately woven into the physiology, behavior, and ecological roles of countless modern species. This legacy is particularly striking in birds, but extends far beyond them, a testament to the enduring influence of these prehistoric architects of life. Foremost among these modern inheritors are birds, the living dinosaurs. Their DNA, anatomy, and behaviors reflect a direct lineage to theropod dinosaurs, carrying forward remarkable superpowers such as powered flight, sophisticated vocal communication, and complex social structures. Many attributes perceived as uniquely avian — feathers, hollow bones, advanced respiratory systems, and keen vision — are in fact deeply rooted in dinosaurian evolution. The aerodynamic feathers that enable flight, the hollow pneumatic bones that reduce weight, and even metabolic traits like endothermy all trace back to dinosaur ancestors, elucidating how evolution conserves and refines superpowers across epochs. Beyond birds, the dinosaurian legacy influences various physiological and behavioral traits in reptiles and mammals. For example, the osteological adaptations seen in some modern reptiles mirror the bony crests and frills of ceratopsians and other marginocephalians, hinting at convergent evolution or ancestral traits shaped by similar environmental pressures and communication needs. Furthermore, the evolutionary development of complex sensory capabilities in dinosaurs, acute sight, enhanced hearing, and olfactory prowess, is echoed in contemporary predators and prey alike. Many mammals, reptiles, and birds exhibit sensory adaptations that parallel those of their dinosaurian forebears, underpinning survival strategies honed through millions of years. Behaviorally, dinosaurs' social superpowers, herding, parental care, display, and communication, find clear counterparts in modern animal communities. Social structures in elephant herds, wolf packs, and bird flocks reflect principles of coordination, cooperation, and communication not unlike those inferred in dinosaurs. Parental investment, cooperative breeding, and complex mating rituals observed in today's animals reveal the deep evolutionary roots of these behaviors. Additionally, the structural and metabolic adaptations pioneered by dinosaurs inspire biomimetic research in fields like robotics, materials science, and medicine. Insights from dinosaur bone strength and flexibility influence engineering designs, while understanding dinosaur metabolism informs comparative physiology and evolutionary medicine. Importantly, the resilience traits that allowed dinosaurs to adapt to diverse environments, such as thermoregulation, metabolic versatility, and regenerative capacity, reside implicitly in many contemporary organisms. These biological strategies highlight consistent themes of adaptation, crucial for survival in changing climates and ecosystems. This legacy illuminates an evolutionary continuum. Dinosaurs were progenitors of a lineage whose superpowers shaped the natural world profoundly. Every fluttering songbird, every predator's keen eye, every social mammal traces echoes of dinosaurian innovation. As our exploration concludes, we step into a realm of imagination with speculative evolution, contemplating worlds where dinosaurs persisted and continued to evolve. This exercise in creative science not only honors their enduring legacy, but also deepens our appreciation for the vast potential of life's adaptive power through time and possibility. Imagine a world where the cataclysmic event that wiped out the non-avian dinosaurs never occurred, where the asteroid impact that transformed the planet's ecosystems 66 million years ago was absent or less devastating. What might have unfolded in the subsequent epochs? How would dinosaurs have continued to evolve and adapt? Speculative evolution invites us to explore these mesmerizing possibilities, blending scientific evidence with informed imagination to envision alternate evolutionary paths where dinosaurs remained rulers of land, sea, and sky. If the non-avian dinosaurs had survived, the Mesozoic landscapes would have transitioned more gradually into new ecosystems shaped by continuous dinosaurian evolution, rather than the abrupt faunal turnovers that heralded the rise of mammals. The enormous ecological niches vacated by dinosaurs would have remained fiercely contested, possibly delaying or reshaping the evolutionary trajectory of mammals, birds, and other groups. Among the largest dinosaurs, sauropods might have continued to increase in size and diversify, evolving specialized morphologies to exploit diverse vegetation types and habitats. Some speculative models suggest sauropods could have adapted to increasingly forested or even cooler climates, developing insulation or modified metabolic processes reflecting changing environments. Their gigantism would continue to influence flora, shaping forests through browsing and interactions. Theropods, the carnivorous lineage to which birds belong, present particularly fascinating prospects. Continuing evolution could lead to more sophisticated hunting strategies, increased cognitive complexity, and the emergence of new sensory and communicative adaptations. Some might have developed enhanced social behaviors reminiscent of modern pack hunters or advanced vocalizations for intra-specific communication. Flight would have remained a significant evolutionary theme. Feathered theropods might have diversified into myriad aerial niches: gliders, sprinters, powerful flyers, or even aquatic flyers. Pterosaurs, having survived alongside birds, might have evolved new strategies for aerial dominance or aquatic foraging, contributing to a dynamic aerial ecosystem. Marginocephalians and ankylosaurs, well adapted to defense and herbivory, could have evolved new armor types, weapon structures, or social behaviors, reflecting both predator pressures and environmental changes. Desert adaptations especially might have intensified, with complex physiological traits enabling thriving in extreme habitats. Symbiotic relationships and multi-species ecological networks would likely have grown increasingly intricate as diverse dinosaurians occupied overlapping niches and varied trophic levels. Such interdependence would drive evolutionary novelty, sustaining stable and productive ecosystems. Moreover, the evolutionary experimentation witnessed in feather types, metabolic strategies, and behavioral innovations, such as parental care or communication, would continue to enrich the dinosaurian lineage, possibly producing even more astounding physiological superpowers. While speculative, these trajectories find support in the observed plasticity and resilience within the dinosaur fossil record, and in analogous evolutionary patterns seen across Earth's history. The potential timelines and pathways are constrained by ecological realities, but unlimited in their creative possibilities. However, the presence of large and dominant dinosaurs might limit the spread and diversification of mammals, birds, and ultimately humans, profoundly altering the trajectory of biodiversity and planetary history. The world's landscapes, climates, and biological communities would reflect a continuing Mesozoic influence, shaped predominantly by dinosaurian evolution. Speculative evolution is a powerful tool that ignites our imagination while grounded in scientific principles. It invites us to consider life's adaptability and evolutionary potential, revealing a universe of possibilities where mass extinction events are not certainties but inflection points, and where life's forms endlessly adapt, diversify, and flourish. As we close this grand exploration into the superpowers of dinosaurs, it is humbling and inspiring to reflect on their enduring legacy, one that bridges ancient worlds and modern life, and one that continues to invite discovery, wonder, and deep curiosity about the past, present, and future of life on Earth.